Today I'm gonna study Pixi JS event system, and I solved the React-pixi problem. I was really happy about that. I'm gonna show like what the solution is, and I was happy about it because not because I solved the problem, because I think I had the correct intuition, and that's why I'm happy is because like the intuition that I had is correct, and then I went through this whole journey of studying the source code and trying to understand. So I solved in a way that makes it clear to me that my understanding is correct, which feels pretty good, to be honest. I think I forgot to put the chat there. But I think the solution that I found is not the optimal one, so I'm still thinking about it, whether or not today is better to try to find a more optimal solution or to start studying the Pixi event system, because next challenge that I'm gonna have is to figure out how to handle two events at the same time, because I have the events on the Matter.js library that are gonna handle the interactions, and I might have to do something completely different, which is not even use the Pixi viewport. But I think this is the point that this is the reason why I'm happy about solving it, because the point of solving the problem is not. So I went with that solution because if that was the point, I think I could have solved way before. I didn't even need to spend the time studying React source code because I had the correct intuition. So probably the solution that I would attempt first would work, but then the issue is I wouldn't have the understanding that I have now, and that's the thing. So after going through all this process, studying the React code, which I still don't understand really well, to be honest, I don't understand the lanes and the nuances, but I'm hoping that through the stuff that I build now, I'm going to be able to use that to study React again and like increase the understanding, become better and better over time. But you can see now that it doesn't fuck up the thing. Also, I'm gonna put music for myself, and I'm not gonna put music on stream because they're cutting the stream. Like before, they would cut the live stream, but the recording would have the part. But last time, as soon as I got to a playlist that had probably the copyright triggered, they cut the stream, and then the recording doesn't exist, like the rest of the part. So last time I spent around 2 hours, I think, or something like that, and here there's only 1 hour. Yeah, so they cut the stream, which is understandable, but kind of sucks because like I obviously don't care about monetization on these videos because I don't even have 1,000 subscribers, so I can't even monetize. So, but I think from YouTube's point of view, they have to cut it because of copyright issues and stuff like that. But I think that that kind of stuff should probably change in the very near future because of AI. Like I don't see, it doesn't make a lot of sense to me. Uh, but maybe it does because on the big platforms they have a way to see. But then like I think over time it's just gonna be more and more people producing content, and then you're gonna have AI, and it's gonna be almost impossible to. But maybe they can use AI and then becomes the whole arms race thing. But yeah, who cares? So I'm gonna put music for myself here. So the solution is very simple. It's just to put this line of code here. So pretty much I spent almost 3 weeks, I think, just to put this line of code here. And what this does is just unmounts the components before before the app gets destroyed. So it makes the effects on the Pixi custom fiber, the custom React compiler, Pixi fiber. It triggers the events, the effects, and then the effects make the components unmount before. And you can see the console logs here are different now, because right after it mounts, and then it mounts the parent. And I think this is not a problem with Pixi itself. It's another thing that I thought about. This is a fundamental problem with React, I think. but it might not be a problem, it might be a feature, because the thing is I don't understand really well how it works. But I think the issue is that React doesn't synchronize custom renders in the correct way. And the problem is that when you have a custom reconciler, it's gonna depend on what point does the person puts the reconciler at, because the reconciler is gonna be part of the state management of the previous one. So it's kind of like you're nesting event loops, let's say. And it's a problem of synchronicity because they have to be synchronized in the correct way. And if you're only using one renderer, then React does that for you. It always mounts the children before it mounts the parents, if the children are dependent on the parent, obviously. But when you put the custom reconciler, it creates this dynamic where, depending on where you put the custom reconciler, is going to fuck up the cycle. And that's the issue here with the React-pixi library. And then when you do this, it fixes. But there's still a fundamental issue with React. And I think I'm going to, because it's very interesting, but then again, it's one of those things where, like, there's always this balance between how many things I can focus on. And so, like, from my curiosity, I want to know, because I think there's a, I thought about a path. I'm not sure if I should share or not before I do it, but like I thought about a way to create a framework that's going to be better, but it's going to be very hard as well to do it. So I'm not really sure if I'm going to follow that direction. And it's going to be interesting to study the other frameworks as well. But first I have to create all of this stuff, and there's still a bunch of challenges I had. So now the issue is that even though I have this stuff here, the events are on the canvas, and I lose the ability to have the events on the elements themselves. So that's what I think I'm gonna have to go with another solution other than using the Pixi viewport. Or I think that's what I'm gonna do right now, which is study the Pixi viewport library to understand how they are creating the events. I think I already studied a little bit, and I have some tabs open. Maybe I should close everything else now. Feels kind of weird to close everything because I spend a bunch of time with all of them open. But it's, yeah. So I think I'm not gonna use for now. So it's probably better to close everything and then open them again and just focus on the Pixi viewport stuff. So I think the first thing that I can try is just change the event names. I think I downloaded Pixi viewport locally here, so I can make changes through the source code. And I think the first thing that I'm going to try to do is change the Pixi viewport source code. And yeah, I have the matter.js source code didn't work really well because it's giving me a warning there because of the constraints. Like when I download locally and try to use locally, I think it's because of the way that they did the imports, which a lot of libraries do it that way, but I don't like it very much. But there's obviously a reason for it. I think it's because when you're creating libraries, like especially if there's going to be things that are very complex, the way that it evolves is you don't know everything that is going to happen before. So the issue they have, I think, is that if you create everything under the same structure, it becomes rigid, and then you can't scale very well. So what people do is just create a bunch of different libraries that work together. So it's more like you're creating different modules, and then you're putting these blocks together, and that's the overall library. I think that's how Pixi JS does it, and how matter.js does it. But the problem with that is that it gets very confusing when you're trying to learn, because there's a bunch of imports everywhere, and you have to follow this structure of classes. It's kind of annoying. So when I download matter.js locally and try to use matter.js, it gives me a warning because it's missing or an argument is incorrect here. In the mouse, I think. Mouse constraint. Yeah, here. So I think it's probably better to try to change Pixi viewport code first. And I think the first thing I'm going to try to do is just change the names. Maybe the other thing I was thinking about is that the reason why I think this is not a very efficient solution is because you're just flushing all the effects. So there's no nuance to it. And what I want to do is just unmount the components that are using the context for that, because those are the ones that are going to break or introduce a memory leak to the application. But the problem with, and this is the thing that I'm not sure, because it might be better to just flush all of them, because if you leave some of them, there's still going to be memory leaks, even though it doesn't give a warning. But I think one thing that you probably could do is just console log the children, and then through the children you call the function, or try to access the function, and then this is the thing that I have to search, because I have to see if when you put functions inside of other functions, are those functions going to be part of the object that is the function in the source code of JavaScript or not. So the same way that each function has a prototype object inside of it, and you can access a prototype object to create another function. That's going to be like how classes work in JavaScript. Does that work in the same way when you have another function inside of a function? So like the question is, can I access the hooks inside of the functions by accessing the part here or not? And if I can't, then it's going to be very tricky, I think. Because if the only thing you can do is run the function, then it's going to run the effects, and there isn't a way to check, I think. Like to compare the props to see if there is a dependency or a difference, and then only after that call the effects, or call the function. So essentially do a diffing algorithm before you run the function. But I don't think there's a way to do that. But maybe I should focus only on fixing the events now, and then I'll come back to this later. Because I think I spend enough time, like now I understand what is going on and how it works, and I also found a solution that works. So the other thing that I can do is obviously just comment that line out and then put something that only removes the components that give a problem. So the custom Pixi viewport, figure out a way to just unmount that component. And this is the first solution that I was thinking about, but it wasn't satisfying to me because I didn't understand how it works. So I felt like I had to go through the whole process, which I'm happy I did. But the solution would be to pass something to the component here, like pass as props maybe, or something like that, to this component, like a reference to the custom Pixi viewport, and then I would have access to the ref here in the class. And then I could just mount that class specifically when the component amounts. But it's obviously not good because it doesn't solve for every case, I think. Just for very specific. Put some other music here for me. I think I'm gonna do the Italian thing as well. So let's think. Also think I don't need this. Yes, flush. The thing that is concerning is that I remember reading on one tutorial or article that this function is not very efficient. Like there was a disclaimer there somewhere that you should only use this with caution because it's not very effective. But I think it's not that big of a deal because it's only going to impact the places where you have this stage component. So I'm not sure if it is that big of a deal. And the component only mounts and unmounts two times when it's initializing the application. Every other update is going to be the component did update function that runs and the other functions that are related to that, but then it doesn't trigger the onMount. So when you're creating new graphs, it doesn't do anything. Only when you switch pages, I think, it triggers the component will onMount. Yeah, I want to get rid of this problem as well with the events because I think that the most interesting part is going to be the compiler. I'm very anxious to start working on that because I think that's the thing that's going to be very interesting to do. Just parse the file and then see how it can translate the file into a visualization. I think that's going to be very interesting. And there's like a billion ideas that I have after that of all of the possible things that I can do once that's possible. But I have to handle the events first. And the events are like kind of annoying. Yeah, first fix this thing with the event, the overlapping of events. Then I have to fix the way the graph works because obviously it's very shitty here with the lines. So that's another annoying thing. That might take a lot of time. And then after that, I think it gets really interesting. Also, after that, I think I'm gonna change the whole uh, layout of the website. Also, another annoying thing because what I want to do is like I want to create an IDE here instead of doing like this. Like put the files here on the side in the same way that the VS Code is, or uh, Sandbox or whatever the other sites that have these IDs. I want to do exactly that, where you can move around the canvas. That's going to be very hard as well to implement because you want to make it easy as possible, like to give the experience at least like because I think I'm my main customer, let's say, because I'm gonna use this all the time, I think. So what I think about what would be useful for me would be if I had the same experience that I have when I'm coding here, but then I can see like a bunch of different stuff about the code and how everything's connected. So that's what I'm aiming for, but it's gonna be very challenging, I think. Like there's several different things that I have to think about. Fuck. To go right back. I think I already stepped through this sometimes. Probably what I should do before is just I'm gonna do the same thing that I did with the React source code. I'm just gonna use the debugger and I'm gonna step through everything. And that's probably the best way to do it. Maybe you should do a flowchart as well. But I think that, like this time, the other time I did it with flowchart before, and then I stepped through after. Because the reason why didn't want to use the debugger is both because I didn't know very well how to use it, but it's also because like I wanted to understand the source code in the context that it is not only when like after it's transpiled by Babel and Webpack. I wanted to understand like how from the standpoint of the person coding the library itself, because I think that's better because it allows you to understand like to get a glimpse of how they might have thought about it creating the library instead of just seeing the final version where um, everything's already transpiled and is a different structure of the files and the organization of the whole thing. But I think that's probably better to do with the debugger first because then you know like what you look for, what's useful, and what's related to what you're doing. So I think this time I should probably put a bunch of debugger statements here and then step through with the developer tools and then after that do the flowchart if I decide to do the flowchart. Just see how everything's connected. I think the main thing that I want to know is like should probably write down the events. I think I'm gonna create a folder for this. I should put it inside of the React one. I think what I'm gonna do is write down a viewport versus matter. Probably put on the same one. Because I want to see, and then the first thing that I'm going to do is try to change the names of the events on the viewport. But the thing that is tricky about this, and that I remember, is that they are using the event emitter, I think, library, like on the base class, let's say, that all these classes inherit from, which I think is the container or something like that. And the issue with this is that it's very hard to know like, at what points it's receiving the events and at what points it's emitting. It's not clear in the code. And there's a bunch of different classes involved. So that's what's challenging. So let me think about it. But first, I think probably the first thing that's useful to do is just to remove the debugger statements of everything. And then puts only debugger statements on viewport. I think I want to leave this console log. Maybe I should remove the console logs actually. It's gonna be annoying to. I'm probably gonna put other console logs. No, I'm gonna remove the debugger statements first. Oh, I can also replace. I forgot about this. Just do this. Yeah, there we go. And now this is gonna be an issue. Because I'm gonna have to remove all of the events here as well. And I figure out you can press F8 here is much better. F8, F10. I'm gonna remove all of this because it's gonna be very annoying to step through all of them. This one was one of the most annoying things about studying React, is just you have to step over, because you can't really go fast, because then you might risk skipping something important, and then if you skip something important, you have to run everything back again and start from the beginning. It's very annoying. So that's the reason why I put all these breakpoints. But then, like, you have to press F8 a lot in the beginning, because it traverses the tree a bunch of times, and for each node that is traversing the tree is gonna do the work loop cycle, which is begin work, I think. Begin work, then I forgot the other ones. That I think at the end is finished work, but in the middle I forgot which one. What's the name of the thing? Maybe it's complete work. Yeah, begin work, then complete work, and then finished work, something like that. And I definitely think that there is a better way to do. There's probably several ways to improve React, both on the performance and on how easy it is to understand the code. But like the thing is, like, it is very impressive what they were able to do. So because it's obviously a lot easier to look at something and then see the problems instead of doing it yourself. And I think that a lot of the problems that probably coding in general has, like all the languages and all the frameworks, is that like the issue is that the way that they evolve, because like it's kind of like a big corporation where like in the beginning you don't know everything that is going to happen, so you start building things in a certain way, but then based on other stuff that happens, you have to like build on top of the stuff that already was there. And it's like the more and more you build on top of it, it becomes like worse and worse, because it magnifies all the problems that you had in the beginning. But because you can't really change the beginning completely, because already everything has a lot of momentum and mass, then it starts becoming worse and worse over time. I think that's one of the reasons why human beings don't scale very well. It's very hard to coordinate, and I think is related to the relationship between matter and gravity, because like an informational structure is the relationship between matter and space-time, I think. So matter in the electromagnetic field created an informational structure. So the bigger corporation gets, the more gravitational force it has, and then the mistakes compound themselves. And because by definition you're not smart enough when you start something, because if you were, you already have the problem solved. As the time evolves, it generates gravitational force, but then is unbalanced because the stuff that you created is not in alignment with the whole. So there's always this effect where, but then obviously the generation of information is going to be to try to approximate the line of the nuances. So it's like always trying to correct itself and improve, and that's the feedback loop system, I think. But it's always easier to, from the outside point of view, to point mistakes. And that's also like beneficial for people because of your limbic system. Like you're always trying to rationalize. So you create devils and angels outside of yourself, because you're the one that take responsibility and spend energy. So most people, 80% of the people are going to criticize, and 20% of people are going to do. So it's always easier to criticize. It's easy to sit here and look like, oh, this shit, this code is shit. React is overblown. There's a bunch of stuff like it's not very good, but it's a lot harder to be the person doing the actual thing. So. I have to remove from here. I'm just gonna step through this now. I'm gonna remove all of this so I can do the same thing for the Pixi view part. Maybe I should talk about the stuff that I'm thinking about, because I'm not really sure if I'm gonna have the energy to do it, or if it's gonna be deviate from my focus too much. And I also think that it's one of those things where it's really easy to say, but it's a lot harder to do. It might be impossible, or not impossible, but impractical to do it the way that I'm thinking about it. Yeah, now the problem is that I'm gonna close all of this stuff. So the other breaking points I'm gonna remove as I'm going through the Pixi view part stuff. I'm just gonna close all these windows first. So let me think. I think I'm gonna put inside of the constructor instead of putting inside of the outside of the component there. The first one. And then I'm gonna put maybe here. Oh, I always forgot to mark the points so I can go back. This is this one. And obviously I need to put on these classes as well. I think I'll see whether or not I'm gonna remove the other console logs once I'm stepping through this. Just see if I'm gonna console log anything here. I think I don't really need to put inside of there. Maybe I'll put another one here. There's other stuff that because they changed the events for true interactive. So I had to change this line here. Yeah, but I think I left like this, probably it works. I think this just sets up the events, but it probably doesn't make sense to put debugger points here because I'm gonna step over or step into anyway, so. I think I will put one on each class. Also, I'm gonna like, after I step into with the debugger, it's probably gonna go, it is gonna go through the other classes. And then as it's going through the other classes, there are gonna be things that I think are interesting, and then I put debuggers on them later. So I'm just gonna put one on each one here, and then I'm gonna start stepping over. I think I'm gonna talk about what I'm thinking because I already made a tweet about it. Also on Twitter, I'm thinking just posting stuff that I think about from time to time that I think is interesting. It's like not very well thought out stuff, just like an interesting thought comes into my mind, and I think, wow, like I should tweet this to remember this later. That's kind of how I've been thinking about it. So sometimes I tweet stuff like this, but yeah, so like the way that I'm thinking about the React stuff and what I think could be improved. And there's also an interesting thing that I saw about this on Twitter as well, that someone was talking about how they were able to figure out how a language model thinks in some aspect. Like they asked the language model, I think, to add two numbers, and then I didn't read too much into it, but from the conclusions they got is that the large language model was using fast Fourier transforms to add two different numbers, and I thought that makes a lot of sense, and is related to the stuff that I'm thinking about here. Because if you think about it, everything is like a wave, and then this wave becomes geometrical patterns, because a wave is more like a spiral, because it's three-dimensional, at least from the reference frame of the perspective of a human being, which has 4 dimensions. So like on the 4-dimensional plane, let's say, which is space-time, you have a wave, which is a spiral, and the spiral is interconnected with all the other spirals, and that creates a multifractal geometry. So the way that I think about the DOM now is that like the fundamental principles are the state, the events, which is the stuff that is going to change the state, and the structure of the hierarchy of cause and effect relationships between those things. So it's like the same thing that happens in space-time, I think. That's why I think that the DOM is very analogous to the way that the space-time works, because it's pretty much the same thing. So, and it's a reflection of hardware as well, because hardware is the same thing, where you have a hierarchy because that's the structure of time. Because entropy implies that there's the essence of things is to always go to disorder, because the definition of order is just a relationship between the reference frame of now and the reference frame of the future. So because of the nature of probabilities, there's always going to be more probabilities for disorder than for order in relationship to a reference frame. Because whatever is considered order to the reference frame is biased towards the reference frame. So there's always this balance between chaos and order, and that's the essence of reality, which is a multifractal conversion in symmetry. But there's always these relativistic symmetries that make up the structure of matter. So the symmetry itself is a hierarchy because that's the essence of time, and the DOM represents that because it's a multifractal hierarchy. You have the main hierarchy of the application, which is the DOM tree, and inside of that you have other trees that make up the multifractal pattern. And each part of this thing has a state. And this is something that I was thinking about as well, that I'm not really sure if it makes sense or not, but I think the essence of space itself is the hierarchy of updates, because the notion of distance is the notion of the priority of updates. Because if you think about it, the distance is correlated with cause and effect relationships. So if you think of something that is further away from you, what that implies is that that thing gets updated less, let's say. It has less priority on the update system that makes up your field of view than something that happens right in front of you, because that's the way that life travels through space. So it is a hierarchy by nature, because you are a point of view of ego identity that creates a hologram that is the essence of space-time, which is a self-fulfilling prophecy in some ways. But yeah, so everything is like a hierarchy interconnected with other hierarchies, and inside of these hierarchies you have the relationships of cause and effect. And cause and effect are the event loops, and the event loops, when they're triggered, they create this cascading effect of what's going to happen in the structure of the tree, which is the flow of data. So the flow of data, the events, and the hierarchy of the tree are all interconnected to create the perception of the movement of the pixels that make up the application on the screen. So the essence of everything, and the point that I'm trying to get, is that React and any other front-end framework is going to be like a structure, a geometrical structure that allows you to create a hierarchy of information through event loops. So I think that React itself, the point that I'm trying to get with this is that React itself and other frameworks are just fast Fourier transforms with Lagrange interpolation. I think that's the essence of the front-end application. So I think that there must be a way to implement fast Fourier transforms with Lagrange interpolation in order to synchronize the updates of events on the DOM. And that's going to determine the hierarchy of cause and effect relationships that change the state of the applications. And inside of this, there are going to be multifractal patterns that are synchronized with reality, let's say. So, yeah. But obviously, I'm not really sure if that makes sense or not. And it's obviously a lot easier to talk about it, because then the challenge is like, how do you create, because there's like these nuances on the way that the state is handled. And that's what I think I'm trying to get at, like with this stuff that I'm doing. It's like, how can you abstract away all of the bullshit that exists, which is the words that we have to use in order to coordinate ourselves, because the words are not fundamental. They're just a reflection of the culture that you exist, because it's interconnected with the relationship between the collective consciousness in space-time. So the computation of human mind creates the words, which are the concepts which the binaries are going to become. So the structure of abstraction becomes a reflection of human nature, but is not essential, let's say, like different than the laws of physics, for example. I think the laws of physics is more the fundamental structure of the computing itself, which is the relationship between the geometrical aspects of the hardware that creates the informational field. So, like, the question is, how can you abstract all the words? So you can see the fundamental structure of what makes up the state, like how the functions, the if-else statements, and the for loops, for the most part, are going to become the structure of logic, which is a geometrical structure that is going to create the informational field that is going to update the data in order to create this tree, which is the DOM. So if you get that, then you're able to see, I think that's, you're able to think about how can you build something that is going to capture the essence of the event loops and the hierarchy of the cause and effect relationship between event loops, which is the nature of the DOM, which creates the hierarchy, because like components inheriting other components. That structure itself is just saying what is the cause and effect relationship of this application. So in a way, you can think about context as being like kind of a wormhole, let's say, or a quantum entanglement, because sometimes you need to, like, there's a different relationship between cause and effect than this, because like perception is always, I think, a self-reflection. So like it's not always linear because it's four-dimensional. So, and I think that might be what contexts are, like kind of black holes, kind of like black holes. Obviously, I have no idea if what I'm saying is correct or not. Maybe I do need to put a debugger on the application, because the application creates the events. I just realized that now. What is the thing is the relationship between the application and the events, the Pixi viewport, is that I'm passing the application as an argument. So the event system is from the application itself, not from Pixi viewport. So I have to understand both the event system from the application and how Pixi viewport changes that. So I think pretty much if you had fast Fourier transforms on, like if you imagine each component as being a fast Fourier transform, and the application is the connection of fast Fourier transforms, which is going to be sine or cosine waves, and the state management is the synchronization between them. So the state management is Lagrange interpolation over the fast Fourier transforms, which are the components of the application. And that over time is going to create the structure of information, which is a hierarchy, which is the same way that the hardware works. So there must be a way to create a framework that creates components based on fast Fourier transforms and then synchronizes them based on Lagrange interpolation. But the problem with this, obviously, is all the logic that is going to happen inside of a component itself, because that's going to be a fractal pattern, because the logic is going to follow the structure of spacetime, which is a multifractal object, I think. And then because of the nuances, I think that this is going to be the evolution of information in functional components. The other thing that I was thinking about is that, like, the essence of life is figuring out where the line is, because the line has infinite complexity. So all the problems everyone has is always on the line, because the line has infinite complexity, and that's the evolution of information. And that's the essence of spacetime, because the line doesn't exist. It's like a self-fulfilling prophecy, because there's always infinite potential. So where the line is always relative to the observer, and the relationship between infinite amount of observers creates the hologram of spacetime, which is a self-fulfilling prophecy in relationship to the identity that creates the illusion of separation between self and observer and what's being observed. No, that's the issue. ChatGPT is too old for this. Oh fuck. I think I'm gonna run this again, because I wanted to see in the first one what happens there. Yeah, this one. I don't understand how it jumps from that to, because maybe it's because, oh no, this is inside of the application and the constructor itself. I thought it was initializing the constructor, the container automatically, but no. As I thought that I skipped the part that is going through the container, but it's just Webpack stuff. Oh no, now it goes. So now it's gonna call this display object. And this calls the events emitter. But I think that's kind of like how Pixi JS works. You have the event emitter at the base of all the classes, and everything is done with this display object as well. So like the bottom is just the essence of the calculations that you're gonna have to do to move objects around the canvas using WebGL. And then with the further away you go in abstraction, it's gonna become more specific to the exact thing you're trying to render. I think that makes sense. So every class has the fundamental blocks of the calculations, but then once starts becoming specialized, the classes deviate, so, and obviously that's why you have different classes. But I always struggle to understand event meters. Transform, I think, is from to coordinates, to calculate coordinates. But I don't understand really well. We have world transform, local transform. They're both matrices. Position scale, pivots. It's obviously going to be to calculate the references of the thing. The reason why I'm not really sure about the stuff that I was talking about before, that the thing that made me think about this, I think, is WebGL. Actually not. I thought about this and then I thought about WebGL after. Because the thing is that in WebGL, like the same stuff that, like the notion of distance is being created by the differences in the scales of the numbers based on the point of view, the field of view thing. But the difference is between that and what I'm thinking about is that in that case, everything is updated simultaneously. The only difference is the scale at which they are updated. But I think space-time doesn't work exactly like that. I think on space-time is not a difference in the magnitude, let's say, is also the difference between like the delay. So it would be like kind of a field of view, but the difference is that there's also the delay of how the further away an object is, the longer it takes for it to be updated in your sense of reality, let's say. So like, for example, the sun, whatever happens at the sun is like 8 minutes ago when it gets to you. So like because it's further away, there's a longer delay on the update of your reality. So it's both that and the thing about magnitude, that the sizes are obviously different. So the calculation of what each pixel is going to be is different, the numbers, because of the field of view thing, because of the curvature of space-time, I think. But yeah, I don't know. It's difficult to reason about this because it's always relativistic, I think. Because it depends, your sense of scale and the essence of the abstractions and your imagination is always going to be a consequence of your perception over the distances of objects and your sense of unity and separation between things, which is already like a consequence of the structure of your concepts. So that's the problem. Because the notion of distance in mathematics itself is an assumption over the relationship between matter and space. And I think Donald Hoffman talks about this, and I think the way that he put it, obviously I'm not gonna do a good job to exactly say how he puts it, but I think he says something along the lines that like the point of science is not to figure out everything, is to over some set of assumptions should go somewhere. And I think that's a very much better framework to have. So it's not like you're figuring out the absolute truth. You have some assumptions, and then over those assumptions, you construct an informational system based on your abstractions that allows you to manipulate reality. But the problem is that people forget that there's always the assumptions behind. And I think that the assumption is the essence of mathematics, because it has to be, because the notion of equality, it's already like implying that there's a connection between past and future, because that's what equality means. So when you're saying that something is equal to something else, you're saying that your perception of matter in space is connected through that lens of equality. That's what you're saying. So over your reference frame, that's how you perceive something to be equal to another. And that's already has embedded into it the essence of space-time. And that's the problem, I think. And I think that's related to the stuff that I was talking about, the like the relationship between the updates and the perception of space-time. Because embedded into that, there's also cause and effect relationships. Because time itself is the connection of cause and effect relationships, I think. But maybe not. Because if you're implying that, if you are saying that time exists, what you're saying is that the past is connected to the future. So that means that you're following the arrow of causation, and that's the arrow of time, and that's why it's like irreversible. I don't think it's irreversible, but under the lens of physics, it is. The thing is about time travel is that it's not. I think it's not that it's impossible to travel back in time. Is that if you traveled back in time, you would be in a fundamentally different reality. So the essence of the state of the now would change fundamentally. So I think that is always the case that you can always go back in time, but the definition of you going back in time is you forgetting that you were there in the first place. I think that's the thing, because that's the essence of what makes up your experience of that moment in time, is that you didn't know about the future and about the past, and by definition, that's what creates your sense of reality of the now. So it's not that you can't go back, it's just that by going back, you forget that you were here in the first place. Because that's what defines the reality you existed before. This is one I remember stepping over, or stepping into, but it doesn't give anything, I think. That helps to understand how the auto detect render works. It's just gonna loop over this stuff, but it doesn't show this one, I think. That's the problem. Yeah, so before this already passes this class extends instead of the renderer here. We go right back. I think one thing I can do is just put a debugger here. That should be interesting. Just see if at any point it runs that. I think it's on the app class. I hate linked lists. Seems like this uses a linked list to update. It's just very confusing to me. I'm not sure if I step into or click the wrong one by mistake. Let's see if F11 works. I think capture here. I think I'm just gonna step into to see if there's any difference between them, but I think it's all the same. I'm just gonna subscribe to the events. It creates the context based on what you pass there, I think, as a third argument. And then the events, the second. Well, the second argument is the function that is gonna run, and then the first one is the event. But I think it doesn't have to do with the name, probably. I think it's something with the classes. Because it should be custom events in both of the libraries, both in Matter.js and in in Pixi view parts. The first one is the function. Over to this one, I think is the other way. Event, the function, the context. And once is if you want to only run once, obviously. I think it's gonna be the same, because the arguments are not different. And it's interesting that it's subscribing the same function for all these different events here. Step on. Oh, actually, I have to put breakpoints on the Matter.js stuff as well. Yeah, that should be interesting because the Matter.js I haven't looked into. With the Pixi, I remember going over these functions like through the source code. And the question is how to know what exactly is happening. That's the problem. It's like when you, I think I have to put event listeners. How do I know what is gonna be triggered when I when I click the thing? I think one idea is to run the app without opening the developer tools. Then just initialize the visualization and then open the developer tools and then click the thing to see if it's gonna, like, if I can put a debugger on the function that is being triggered once I click the graph. And then I can look at the name of the event and see in Matter.js like what's happening. Because I want to understand why it chooses one library over the other. I think it's because of the order of components. That's another thing you can test, I think. Just change the order. Like if I put the custom components inside of some other components, if I wrap the road around or the mouse components. The issue of that is that it's gonna be annoying to just pass the props and do this stuff. That's kind of why I want to avoid doing that. What I could do is just pass the components from here to inside of here, or like inside of the shape even, or somewhere out inside of the component that is creating the mouse events inside, like after this one, because that way will allow me to see if it's because of the order of the components that is giving a preference to Pixi viewports. It could be that, and it could be because Pixi viewport attaches components to the canvas and Matter.js attaches to the elements in the canvas. So when you click, it's considered as being clicked, as the canvas being clicked and not the element inside. But I'm not sure if that makes sense or not, because the event bubbling thing, but I think I tried to download Matter.js locally and do the stop propagation stuff to see if it's gonna work, but it didn't. Because it makes more sense intuitively to me that it would be the event that gets triggered is the one that is further away, let's say, on the DOM. Because, so for example, like if you have a div wrapping a component, I think the order should always be to trigger the event on the component inside of the div first, and then bubble up to the div, the outside div. I think that makes a lot more sense, because that allows you to have more flexibility. But maybe that's not the way that it works here on this circumstance. Because I think if it did work that way, then, but maybe actually, no, if you worked that way, actually it would work when it's put the stop propagation there, because then the event would travel all the way to the element itself on the canvas, and then once it's supposed to bubble up, you call the stop propagation, and then it doesn't trigger the event on the canvas. So I think if that was the way that it was working, then putting the stop propagation would make it so that the events, two different events work. When you click on the element, you would just move the element or trigger the Matter.js event, and when you click on the canvas, it would trigger the Pixi viewport event. But I think that's not what's happening here. I think that's what's happening is that it's probably because, actually I have no idea if it is because of the order of components here, or because Pixi viewport attaches the events on the canvas itself, and Matter.js attaches on the elements. So the canvas has higher importance, let's say. I think it's more likely that the viewport wraps the mouse, but maybe not. I think I read on the React documentation stuff about this as well, but I don't remember really all. Maybe I should read again now, which is the difference between the event listeners and the events in React. The events in React are like, it's not that they're synchronous, but they don't depend on user input, and the event listeners depend on user input. So there's a difference between the two. but I don't remember really well how React handles the differences. Like, what's the connection between them? I think that intuitively, the connection is that the event listeners are going to trigger the effects on React because obviously it's changing the state. So it changes the state depending on the user input. But then React has the preset preferences, not preferences, but the order that is going to update the stuff, which is going to be through the algorithm, which is just going to traverse the tree recursively. So it goes from the top, flagging everything as beginning work until it reaches the bottom. Then it goes back again up, and then it goes through the siblings as well. And it starts completing the work, I think, based on the diffing algorithm. So what's the fundamental question here, I think? I think the question is, what is the relationship between when the event gets triggered and how it's going to update the components? Yeah, I need to figure out a way to put the debugger once I click on the canvas. That's what I have to do. Because what I want to understand more is the like chain of connections of things that are gonna happen once I click, once the event gets triggered. And depending on where the event gets triggered, I think that React is also gonna handle the same way, which is to traverse the tree, use I don't remember really well. I think it's begin work, complete work, and then finished work, or something like that. Like there's the rendering phase and the commit phase. So I think first is after the event gets triggered, React is gonna begin the work loop, and then it's gonna do that while loop, and then it's gonna call the functions to flag everything that is gonna have to perform work, and it's gonna put on the update queue. And then when it gets time to commit, it's gonna commit everything synchronously depending on what is on the queue. I think that's what's gonna happen. And then the differences are gonna be depending on where the event gets triggered. Is gonna I think the reaction is always gonna be the same, which is the way the React handles the effects. But depending on where the event gets triggered, is gonna change the order that the effects are. That the update queue is constructed, let's say. Because depending on what kind of event it is, has higher or lower priority. But maybe the user event's always highest priority. I think that's probably the case. So it's probably going to be always the same. And it's more about understanding how JavaScript is going to decide the priority on the event loop in the micro tasks and macro tasks. So I think probably the best way is to find a way to put the debugger on after I click the canvas. How can I make that happen? Let me think I'm gonna go over this a little bit and think about it. Yeah, this part I think is the part that it commits the stuff. I don't remember really well. Like the thing is that the names and the like I have a decent idea of how everything's connected, but the nuances I still like it's not very clear. So, like I understand how it works. And this happens a lot with me, I think. Yeah, a lot of the times I understand stuff, but I can't put into words, let's say. It's very weird. It's just like more intuitive understanding. Let me go back and see, because I wrote down here the order. I think this picture is also helpful. No, it isn't this one. No, this is event bubbling. And maybe I didn't put here. There was an article that had an animation that was very good. Maybe I saved on the favorites. This is from the Jacer video, I think. I don't remember how to say his name or his nickname on YouTube. Yeah, this is the order, I think. I think he did a great job of capturing very well, like what is the essence of the thing. The only issue I had with his videos and trying to understand is that he didn't talk about the nuances very much. And this is the problem with going through the debuggers, because I think it was going very fast between, like, the thing is, like, once you step over the functions, you kind of lose like sense of the how everything is connected, let's say. So on his videos, he's just jumping around from function to function. It becomes hard to understand how everything is connected. That's the only problem. But after I went through the debugger, I think that like his video is very good to capture the essence of what's happening. He pretty much went straight to the point. Yeah, perform sync work route. So the work is the rendering phase, and the commit is the commit phase, obviously. And the commit you can stop, and the rendering you can bail out if depending on the differing algorithm, I think. And the challenging thing that and the stuff that I don't understand really well are the lanes as well. The lanes and the exact order. Because it gets very complicated, because it's going to depend on whatever is happening in the application. So each circumstance is going to be slightly different. So it's very hard to understand how it works every time, because there's a bunch of global variables. I think that's one of the things that probably could be improved, I think. Along with the way, I think that the essence of what I was saying back in the beginning is the stuff, because I think that this perform unit of work, this loop here of the work of the rendering phase and the commit phase, is trying to capture that essence of the fast Fourier transforms and the Lagrangian interpolation. I think that's what these loops are about, and I think there's a much simpler way to connect all these functions into some function that is a lot more simple, let's say. Because what this does is just captures the life of the component, let's say, or like the whole. It captures the fractal pattern of the updates based on whatever's happening. The diffing algorithm is gonna check to make it more efficient, but it doesn't change the structure of the thing. Just pretty much a cycle on a tree, which becomes a spiral through time. And I think what makes it a spiral is probably the lanes and the lanes in the queue. That's what changes the amplitude of the wave function. That's gonna change the state of the components. So there's probably a way to do it that is simpler, I think. But this is the loop: form, begin, then complete, and then commits. And I think the append stuff comes on the commit phase, maybe. I think some of them come on the rendering phase, but the other ones are on the commit phase. Challenge here, and I'm gonna have to run this again. So let me think about it. I think I'll be right back. Think about this. think I'll take a 10 minutes meditation break. It's almost 2 hours. Then I'll keep going. I need to think about. I think I'm also gonna read some articles or go back to. Let me try to find the article that I was thinking about. Think I might have saved on the bookmarks. It was a very good article talking about the event, the React fiber, and how how the states are updated. I don't think I have it here. I think I wanna read. Maybe it's this one. Or it's this one, I think. But he had an animation somewhere, I think. Yeah, the link here. That's the one. So I'm probably gonna read this. I'm gonna meditate for 10 minutes, then read this, and then read some stuff about the events as well. I need to understand the connection between the events triggered by users and the effects on React. There's some stuff on the documentation that talks about this. And like I said before, I don't wanna shit on React and the people that build this because it's obviously always a lot easier to talk shit about something than to actually do the work. Should build this stuff. And the documentation is very good, but obviously there's a lot of stuff, so they can't cover everything, I think. But there's some very good stuff here about events. I think I'm gonna read this again with the text-to-speech thing. I think also I have to put the debugger breakpoints on these components once it creates this stuff. The main thing that I'm trying to figure out is where the conflict comes from and what is happening when the event is triggered. That's the stuff that I'm trying to understand. And I think the best outcome would be if I could use both of them. So Pixi viewport handles the stuff that happens with the view of the camera, and Matter.js handles everything that is related to the objects themselves. And I think doing like this is probably the best way to do it because later on, I think that the complexity is going to scale exponentially over the events that are related to the elements in the canvas, but the events related to the view of the canvas are is going to be the same. So I think it's better to separate them because that way it allows me to have a simple event system for handling the movement of the view itself, and then more flexibility to change whatever's going to happen with the events of the elements. Because the elements are going to be very chaotic, I think, because it's going to depend on what do I decide to do with the elements, which there's an infinite amount of ideas, I think, because it's related to the structure of code itself and several different applications. Because obviously, if I change the languages and if I change the way that what the information I'm trying to capture from the code is going to change a lot. What do I want to do with the elements after I capture the visualization? because I think it's going to be very powerful if I'm able to attach functionality to each node that is related to whatever information I capture from the code itself. But if so intuitively, I think it's better. It feels better to separate both of them. But at the same time, it doesn't feel very good because like you're using two different libraries to handle events. So it's like, I don't know, because they both have different paradigms, I think. Like it's very similar, but obviously different. Because one is built for handling events in the context of a physics engine, and the other one is built just for the view. So like in a way, it feels like they should both be. I should use the same thing for handling the events, because like that encapsulates the events on its own thing. But in another sense, I think it makes sense to separate them because even though they are both events, it's fundamentally different because the functionality is going to be different for both of them. So I think that yeah, the best outcome would probably be to be able to do it the way that I'm doing here now. And then like if I can figure out, because that's the challenge, is that the events are always going to be similar for both of them. So I don't know if I'm going to be able to find a way to have events on the canvas because like for example, both of them use the click event. So if I could figure out a way to just maintain like constant the events related to the canvas, the view of the canvas itself, then I think that's the best because that will allow me to add whatever functionality I want for the elements. But I think that's probably not it's probably not possible, I think. Unless I have both of them, unless I use the library, the same library for both of them, but maybe it is. So I think the fundamental thing that I'm trying to understand is the event emitter. So first, what is the event system that they both use? And then, like, how does the name of the events are related to each other? Because if I can use both of them by changing the names of the events, then I think that's the best. That allows me to have both, like the best of both worlds, let's say. And then it becomes much easier to change the events on the meta.js because I always know, I'm always gonna know what events I can't use because they're being used by the viewport. But if it's something different, then it might be impractical or impossible to use the two different libraries. And that's gonna be more annoying because then I'm gonna have to figure out how to either, and this is the thing. The other option that I have is figure out another physics engine, but that's also gonna be really annoying. And then the most difficult one would be, but I think the best one long term probably, but the most difficult and probably impractical is to create my own thing, like just copy all the functionality that they use for the events, and then I can create my own system and put whatever I wanna put there. That's also an option, I think. I think that's the best long term, but it might be not the smartest idea because then it's kind of like trying to build a car if you're trying to go to the moon, let's say. Like you need a car to go to the moon because the car increases the speed, that's coordination that everyone has to build stuff to build rockets, but then that's not the stuff that you're trying to do. So it's like I want to build a rocket to go to the moon. So the question is like, can I build my own car as well to help me have more control over what's happening? Because the more stuff that you're not in control, it's like more points of failure for your team because then it depends on everything else. So as stuff gets updated, it's like you're creating more points of the more breaking points, because then stuff like this can happen in the same way that like it happened now with the Pixi viewport, right? They change something and then it breaks everything else because everything is connected. So you're losing control. So like the question is how much control you can give, because speed also matters. So I think it's probably not the smartest idea to build my own stuff from the scratch. I think it's probably better to try to figure out how to make them work, but I have to go, like, essentially I'm gonna go over the same journey that I just went through to solve the React-pixi. Probably just gonna spend 3 weeks searching, studying the source code of Matter.js and Pixi viewport to understand really well how they work and how the functionality of everything works. And then in case there's something happen in the future, then I can just, or maybe I can gradually move from the libraries to doing my own stuff by like one function at a time, let's say. There's also the thing, the, the other thing that is good about creating my own stuff is that these libraries, by definition, they're going to be optimized to more cases because it has to be more general because a bunch of different people are going to use it. But if I build my own stuff, then I can optimize fully to what I'm doing. So it allows me to have more, like, to be more efficient than to use the library. Because then I can get rid of a bunch of stuff that doesn't matter for what I'm doing. And I think that's probably the correct direction to go with long term. Because I think it's slightly different than the analogy that I gave, because I think it's more related. It's like, it's not that I'm trying to build a car to create a rocket. It's more like I'm trying to build the material from the rocket is like more associated to what I'm doing, because the physics engine is a key component, I think, of what I'm gonna do, or what I'm thinking about doing with all the visualizations and all the possible things that you can do, the simulations. So yeah, it really depends on the direction that this goes. That's the challenging thing, because it's gonna depend. Yeah, maybe what I should, maybe the best approach is to try to get to the point that I'm building the compiler as fast as possible, because I think that the key essential thing is the compiling and getting the data. I think those are the thing. How to create the structure of the visualization and what ways I'm going to capture the data for the visualization, which is the code. I think that's the essence of what I'm doing. So I probably should try to get there as fast as possible. So just use the libraries for now, and then once I get there, I'm gonna have a better understanding of how useful can I make this, because I don't even know if it's gonna be useful or not. I think it's kind of useful because the thing is that before I didn't fully explore all the possible things I can do because I was very busy with other stuff. So I didn't build the visualizations in the way that I had in mind. So they weren't as useful because they're they were still useful, but not as useful as I think it can be. But to make that very useful is going to be extremely hard, I think, because it's going to require to have a deep understanding of how the interpreters and compilers work. And that's essentially what I'm trying to do, I think. Just to gain more and more clarity over the hierarchy or the structure of concepts, how binary becomes concepts, and that's what programming is. Just creating structure of concepts based on binary. So if we're able to visually see, for example, how a div syntax becomes machine code, and then find the middle line where all of the code is the same, which is probably assembly or variations of assembly. So you can capture the main fundamental structures, and then you can see what is fundamental, and like bring more clarity over what exactly is the difference between different programming languages. I think at the end of the day, is gonna be the fundamental things are gonna be like the stuff that you need to make a Turing complete machine, which is for loops, if else statements and functions. I think those are the three components of everything. I think everything else is a byproduct of that. What we'll call data structure is just a collection of these, and this is the structure of concepts. I think that the thing is that the concepts are a reflection of the computation of the collective consciousness, which is the way that human beings create abstractions based on the impulses of space-time. That's why you have different languages, is because the computation of the collective consciousness is connected with the essence of space-time, which is dependent on the electromagnetic field. That's why you have West and East, and you have different cultures for each one because of the electromagnetic field of Earth. The computation of the collective consciousness is a reflection of the electromagnetic field of Earth and of space-time. So the evolution of concepts is going to be analogous to the evolution of social structures in relationship to space-time, which is going to create programming languages. And the specialization of different programming languages are going to be a reflection of the hierarchy of concepts, but they don't say necessarily something connected with the essence of space-time, which would be the laws of physics, let's say. So obviously there's always this spectrum of objectivity and subjectivity, which is where the line is, and that's the flow of time. So like to gain more clarity, you have to think more about first principles thinking, which is just the flow of time. It's like increasing signal to noise, which is going to be like the funnel of the paradigm of scientific thinking, which is the paradigm of experimentation. So like you want to increase the clarity over the connection between past and future, which is experiments, which is the frequency of computation in relationship to a reference frame. And to do that, you have to remove or clear out the noise, which is just the arbitrary stuff that we build. So for example, each library is going to have different names for each things, because that allows us to have more coordination, because you can understand concepts. So, but I want to see, like, if you remove all the concepts, what's the essence of everything? So, because for example, Matter.js can have very similar functionality to other physics engines, but a very big part of that is going to be the differences in the names they give for each thing, and that's makes it harder to see fundamentally what is the difference, because you're always thinking about the names of the things. So if you could remove the names and just see what is the fundamental logic that makes the two different libraries different, then I think you can think more about the geometrical structure of the code and how that evolves over time. And then there's going to be a connection with space-time based on that, because the computation is just a consequence of the way the electromagnetic field is structured over space-time, which is the informational field. So doing that's gonna, and that's extremely connected with the physics engine, because in order to get a good representation, you have to emulate the laws of physics very well. And I think that's gonna be, it would be a very interesting component of this, like to be able to visually see a very good approximation of what's actually happening in space-time on the visualization with the code, and how that is connected with the collective consciousness. I think that's what I'm trying to do, because then you can put the economy as well in the simulation, because the economy is just going to be, I think I saw this on Twitter as well yesterday, is just the money that ChatGPT or GPT-4 says that money is information, which is probably getting from somewhere else, but I think I agree with that, and money is the database. So like the structure of the market economy is just a computation of the collective consciousness, which is an exemplification of the reproduction pattern. And the flow of information, which is the frequency of the collective consciousness, is going to be the flow of the computation of markets with the regulation of politics, which becomes a vicious cycle because it's corrupted. Because the limbic system is not powerful enough to predict how the prefrontal cortex is going to change the environment, because it doesn't scale well. So it becomes this vicious cycle and then lacks harmony, which makes it more likely that it's going to self-destruct with exponential power because you can't regulate. So allowing to visualize for how the computation becomes power and is connected through the essence of the collective consciousness. And if you put like blockchain on that, if you try to create a blockchain based on that, then you can, and I think it would make it a lot easier if I could visualize like how is that happening. But in order to do that, you have to get a close approximation of what is happening based on the laws of physics. I think that like the main goal is to figure out what is the frequency of the expansion and contraction that the market economy and the in politics have over time, and how much that is misaligned with an optimal distribution of power between conscious agents, because that's what I think the problem of alignment is. Obviously, it's like a multi-dimensional problem because there's several different things, but I think that most of these things you can't control, so it's not worth thinking about them. I think what you can control is like over a network system, how you can design the network in such a way that the nodes of the incentives of the nodes and the power of the nodes of the network don't create something that shifts towards an exponential distribution over time, because that's going to make it so that the mass of the network in relationship to its power is not balanced. And that's what is lack of alignment. Because the problem is not regulations, is that the agents, the nodes in the system doing the regulation are part of the vicious cycle, because they are corrupted by the power that the network creates. I think I'm going to meditate for probably 15 minutes. And then I'll continue to study this stuff. Also, I was thinking about that, like doing API requests. Like, so human beings are very similar to computers, I think. Like human beings are biological computers, essentially. That the conversations are doing is like the exact same thing as doing API requests. The only difference is that the conversation is through wave functions in the through vibrations in the air, and API requests are through the electromagnetic field in wires. And obviously, you can have like stuff like Starlink, where it's also through the air, and maybe that's the way that things are gonna go. So like a person or a human being, the notion of a human being would be like a data center or something like that that holds a lot of information, and then it creates the sense of identity. But like the thing is that the question about consciousness, whether or not, is not the point that I'm not saying that machines are definitely alive. It's just like it depends on the way that you look at it. But like ChatGPT, for example, would be more like the conversations that ChatGPT has with its users would be more like the conversations that molecules inside of your body have with other parts of your body that is being transferred through blood. So blood is like the wire, and the hormones are like doing API requests. Is the protocols of API requests through the blood system, and it's the same thing with the body, and the protocol of communication has the encryption, which is the geometry of the molecules inside of the body. And I think that's pretty much the same thing. And then it made me think that relationships like marriage and like casual sex is kind of like the same stuff that happens with APIs. So like when you have a front end and back end, it's like you're marrying, and then you have microservices is like pimping. But obviously, not sure if it's like it's not exactly the same. It's different because of the frequency, but it's pretty much the same thing, I think. So like talking to people is the same as doing API requests back and forth. And there's also this like the same protocols where depending on the culture, you're gonna have a different handshake for talking to people. It's pretty much the same thing. Where you have protocols of communication, where you do like you say some stuff, then they're gonna say some stuff back, and then the reason why people the reason why you get the awkward feeling of talking with people you don't know is because there isn't an established protocol of communication yet. So it's like, yeah, it's like the caching system, like doing API requests to a server that doesn't know your IP would be like meeting someone new. But then when you cache their connection on your server, then it becomes like a relationship. And then the structure of the wires and the communication between them is going to determine the geometrical structure of the system as a whole. And it's the same thing with social structures, I think. That the essence of relationships between people is going to be directly related with the computation of the environment, let's say. And then the power of the structure changes and determines the essence of relationship between people in social structures, because it's just a multifractal object in space-time. It is very interesting to think about this. And obviously the question of consciousness is much harder because you can't know, I can't know for sure if other people are conscious or not. And it's the same thing with computer, and I think the line is always arbitrary because it's the whole thing I was talking about in the beginning, where the whole essence of the flow of information is finding where the line is, because the line is not the line happens on the surface, and the surface is the frequency of awareness of an observer. It's going to determine the essence of different objects in space-time. Like the difference between a table and a mouse, for example, is just the parsing of information of a reference frame over the essence, the multifractal essence of the electromagnetic field that makes up whatever you think the object is. And the evolution of the line, which is the relationship between the polarity of the electromagnetic field which is the dense of the frequency of the wave function, is going to determine the essence of the object in spacetime. This is always relative to scales. And I think it's the same thing with machine learning agents and large language models. It's very hard to know whether or not they are conscious, because where you draw the line is always relative to the observer. So what you decide, how you decide something is conscious or not, is always arbitrary to whatever your perspective is at the time. And that's going to be dependent on the hierarchy of concepts that are connected with the geometrical structure of spacetime. So it's the same as a large language model. There's obviously the point, the gradient and the point of the quote-unquote singularity that is going to determine like whether or not a machine is conscious, which is always going to be something arbitrary, because there is no way to prove, because it goes beyond that. But the question is, like, at what point does a data center becomes conscious, or is considered as the same thing as being conscious? Because the boundary between the data that makes up the informational system is like big enough that it's considered its own thing, its own living system. Because if you think about a human being, it's just a collection of API requests from the environment to the electromagnetic field that makes up the illusory sense of identity that the human being has, which is the geometrical structure of its electromagnetic field. It's going to be a consequence of the vibrations in the air and the food and water and everything that gets inside and outside of the system. That's going to determine the computation that the system does, which is going to create abstraction. And I think that the internet is an extent of the imagination of human beings, the abstraction, and it's just a funnel. So that's the essence of the identity as well, I think. It's an asymptote between imagination and what is considered to be real, because it's just a flow of density. It's just a distribution of density. What is real is just more dense than what it isn't in relationship to a reference frame. And that implies the frequency of computation from that identity that parses infinity and creates the illusion of spacetime, which is a hologram, I think.
Inside Fiber, in-depth overview of the new reconciliation algorithm in React. Dive deep into React's new architecture called Fiber and learn about two main phases of the new reconciliation algorithm. We'll take a detailed look at how React updates state and props and processes children. React Fiber reconciliation, 15 March 202019 min red 0 comments. React is a JavaScript library for building user interfaces. At its core lies the mechanism that tracks changes in a component state and projects the updated state to the screen. In React, we know this process is reconciliation. We call the setState method, and the framework checks if the state or props have changed and re-renders a component on UI. React docs provide a good high-level overview of the mechanism, the role of React elements, lifecycle methods, and the render method, and the diffing algorithm applied to a component's children. The tree of immutable React elements returned from the render method is commonly known as the virtual DOM. That term helped explain React to people early on, but it also caused confusion and isn't used in the React documentation anymore. In this article, I'll stick to calling it a tree of React elements. Besides the tree of React elements, the framework has always had a tree of internal instances, components, DOM nodes, etc., used to keep the state. Starting from version 16, React rolled out a new implementation of that internal instances tree and the algorithm that manages it code named Fiber. To learn about the advantages which the Fiber architecture brings, check out the how and why on React's usage of linked list in Fiber. This is the first article in a series aimed at teaching you internal architecture of React. In this article, one wants to provide an in-depth overview of important concepts and data structures relevant to the algorithm. Once we have enough background, we'll explore the algorithm and main functions used to traverse and process the Fiber tree. Next articles in the series will demonstrate how React uses the algorithm to perform initial render and process state and props updates. From there, we'll move on to the details of the scheduler, the child reconciliation process, and the mechanism of building an effects list. I'm going to give you some pretty advanced knowledge here. I encourage you to read it to understand the magic behind the inner workings of concurrent React. This series of articles will also serve you as a great guide if you plan to start contributing to React. I'm a strong believer in reverse engineering, so there will be a lot of links to the sources from the recent version 16.6.0. It's definitely quite a lot to take in, so don't feel stressed if you don't understand something right away. It takes time as everything worthwhile. Note that you don't need to know any of it to use React. This article is about how React works internally. Setting the background link to this section. Here's a simple application that I'll use throughout the series. We have a button that simply increments a number rendered on the screen. And here's the implementation. Less than greater than copy class click counter extends React. Component, constructor, props, super, props, this. State equals, count, 0, this. You can play with it here. As you can see, it's a simple component that returns two child elements button and span from the render method. As soon as you click on the button, the state of the component is updated inside the handler. This, in turn, results in a text update for the span element. There are various activities React performs during reconciliation. For example, here are the high-level operations React performs during the first render and after state update in our simple application. Updates count property in the state of click counter. Retrieves and compares children of click counter and their props. Updates props for the span element. There are other activities performed during reconciliation like calling lifecycle methods or updating refs. All these activities are collectively referred to as work in the Fiber architecture. The type of work usually depends on the type of React element. For example, for a class component, React needs to create an instance, while it doesn't do that for a functional component. As you know, we have many kinds of elements in React, e.g., class and functional components, host components, DOM nodes, portals, etc. The type of React element is defined by the first parameter to the create element function. This function is generally used in the render method to create an element. Before we begin our exploration of the activities in the main Fiber algorithm, let's first get ourselves familiar with the data structures used internally by React. From React elements to fiber nodes linked to this section. Every component in React has a UI representation we can call a view or a template that's returned from the render method. Here's the template for our click counter component. Less than greater than copy less than button key equals 1, on click equals this. On click greater than update. Counter less than button greater than less than span key equals 2, greater than this. State count less than span greater than. Once a template goes through the JSX compiler, you end up with a bunch of React elements. This is what's really returned from the render method of React components, not HTML. Since we're not required to use JSX, the render method for our click counter component can be rewritten like this. Less than greater than copy class click counter, render, return, React, create element, button, key, 1, on click, this. The calls to React, create element, in the render method will create two data structures like this. Less than greater than copy, $type of, symbol, React, $type of. You can see that React adds the property $type of to these objects to uniquely identify them as React elements. Then we have properties type, key and props that describe the element. The values are taken from what you pass to the React, create element, function. Notice how React represents text content as children of the span and button nodes. And how the click handler is part of the button element props. There are other fields on React elements like the ref field that are beyond the scope of this article. The React element for click counter doesn't have any props or a key. Less than greater than copy, fiber nodes linked to this section. During reconciliation, data from every React element returned from the render method is merged into the tree of fiber nodes. Every React element has a corresponding fiber node. Unlike React elements, fibers aren't recreated on every render. These are mutable data structures that hold components state and DOM. We discussed earlier that depending on the type of a React element, the framework needs to perform different activities. In our sample application, for the class components click counter it calls lifecycle methods and the render method, whereas for the span host component, DOM node, it performs DOM mutation. So each React element is converted into a fiber node of corresponding type that describes the work that needs to be done. You can think of a fiber as a data structure that represents some work to do or, in other words, a unit of work. Fiber's architecture also provides a convenient way to track, schedule, pause, and abort the work. When a React element is converted into a fiber node for the first time, React uses the data from the element to create a fiber in the create fiber from type and props function. In the consequent updates, React reuses the fiber node and just updates the necessary properties using data from a corresponding React element. React may also need to move the node in the hierarchy based on the key prop or delete it if the corresponding React element is no longer returned from the render method. Check out the child reconciler function to see the list of all activities and corresponding functions React performs for existing fiber nodes. Because React creates a fiber for each React element, and since we have a tree of those elements, we're going to have a tree of fiber nodes. In the case of our sample application, it looks like this. All fiber nodes are connected through a linked list using the following properties on fiber nodes: child, sibling, and return. For more details on why it works this way, check out my article The How and Why on React's usage of linked list in fiber if you haven't read it already. Current and work in progress trees linked to this section. After the first render, React ends up with a fiber tree that reflects the state of the application that was used to render the UI. This tree is often referred to as current. When React starts working on updates, it builds a so-called work in progress tree that reflects the future state to be flushed to the screen. All work is performed on fibers from the work in progress tree. As React goes through the current tree, for each existing fiber node, it creates an alternate node that constitutes the work in progress tree. This node is created using the data from React elements returned by the render method. Once the updates are processed and all related work is completed, React will have an alternate tree ready to be flushed to the screen. Once this work in progress tree is rendered on the screen, it becomes the current tree. One of React's core principles is consistency. React always updates the DOM in one go. It doesn't show partial results. The work in progress tree serves as a draft that's not visible to the user, so that React can process all components first and then flush their changes to the screen. In the sources, you'll see a lot of functions that take fiber nodes from both the current and work in progress trees. Here's the signature of one such function: update host component, current, work in progress, render expiration time. Each fiber node holds a reference to its counterpart from the other tree in the alternate field. A node from the current tree points to the node from the work in progress tree and vice versa. We can think of a component in React as a function that uses the state and props to compute the UI representation. Every other activity like mutating the DOM or calling lifecycle method should be considered a side effect or, simply, an effect. Effects are also mentioned in the docs. You've likely performed data fetching, subscriptions, or manually changing the DOM from React components before. We call these operations side effects, or effects for short, because they can affect other components and can't be done during rendering. You can see how most state and props updates will lead to side effects. And since applying effects is a type of work, a fiber node is a convenient mechanism to track effects in addition to updates. Each fiber node can have effects associated with it. They're encoded in the effect tag field. So effects in fiber basically define the work that needs to be done for instances after updates have been processed. For host components, DOM elements, the work consists of adding, updating, or removing elements. For class components, React may need to update refs and call the component did mount and component did update lifecycle methods. There are also other effects corresponding to other types of fibers. Effects list linked to this section. React processes updates very quickly, and to achieve that level of performance, it employs a few interesting techniques. One of them is building a linear list of fiber nodes with effects for quick iteration. Iterating the linear list is much faster than a tree, and there's no need to spend time on nodes without side effects. The goal of this list is to mark nodes that have DOM updates or other effects associated with them. This list is a subset of the finished work tree and is linked using the next effect property instead of the child property used in the current and work in progress trees. Dan Abramoff offered an analogy for an effects list. He likes to think of it as a Christmas tree, with Christmas lights binding all effectful nodes together. To visualize this, let's imagine the following tree of fiber nodes where the highlighted nodes have some work to do. For example, our update caused C2 to be inserted into the DOM, D2 and C1 to change attributes, and B2 to fire a lifecycle method. The effect list will link them together so React can skip other nodes later. You can see how the nodes with effects are linked together. When going over the nodes, React uses the first effect pointer to figure out where the list starts. So the diagram above can be represented as a linear list like this. Root of the fiber tree linked to this section. Every React application has one or more DOM elements that act as containers. In our case, it's the div element with the ID container. Less than greater than copy const DOM container equals document. Query selector, hash container, React DOM, render, React, create element, click counter, DOM container. React creates a fiber root object for each of those containers. You can access it using a reference to the DOM element. Less than greater than copy const fiber root equals query, hash container, underscore. React root container, underscore, internal root. This fiber root is where React holds the reference to a fiber tree. It is stored in the current property of the fiber root. Less than greater than copy const host root fiber node equals fiber root. Current. The fiber tree starts with a special type of fiber node which is host root. It's created internally and acts as a parent for your topmost component. There's a link from the host root fiber node back to the fiber root through the state node property. Current state node equals fiber root true. You can explore the fiber tree by accessing the topmost host root fiber node through the fiber root. Or you can get an individual fiber node from a component instance like this. Less than greater than copy comp instance, underscore, React internal fiber node structure linked to this section. Let's now take a look at the structure of fiber nodes created for the click counter component. Less than greater than copy, state node, new click counter, type, click counter, state node, new HTML span element, type, span, alternate, null, key. There's quite a lot of fields on fiber nodes. I've described the purpose of the fields alternate, effect tag and next effect in previous sections. Let's now see why we need others. State node linked to this section holds the reference to the class instance of a component, a DOM node or other React element type associated with the fiber node. In general, we can say that this property is used to hold the local state associated with a fiber. Type linked to this section defines the functional class associated with this fiber. For class components, it points to the constructor function, and for DOM elements, it specifies the HTML tag. I use this field quite often to understand what element a fiber node is related to. Tag link to this section defines the type of the fiber. It's used in the reconciliation algorithm to determine what work needs to be done. As mentioned earlier, the work varies depending on the type of React element. The function create fiber from type and props maps a React element to the corresponding fiber node type. In our application, the property tag for the click counter component is one which denotes a class component, and for the span element it's 5 denoting a host component. Update queue link to this section. A queue of state updates, callbacks and DOM updates. Memoized state link to this section. State of the fiber that was used to create the output. When processing updates, it reflects the state that's currently rendered on the screen. Memoized props link to this section. Props of the fiber that were used to create the output during the previous render. Pending props link to this section. Props that have been updated from new data in React elements and need to be applied to child components or DOM elements. Key link to this section. Unique identifier with a group of children to help React figure out which items have changed, have been added or removed from the list. It's related to the lists and keys functionality of React described here. You can find the complete structure of a fiber node here. I've omitted a bunch of fields in the explanation above. Particularly, I skipped the pointers child, sibling and return that make up a tree data structure which I described in my previous article. And a category of fields like expiration time, child expiration time and mode that are specific to scheduler. General algorithm link to this section. React performs work in two main phases, render and commit. During the first render phase, React applies updates to components scheduled through set state or React. Render and figures out what needs to be updated in the UI. If it's the initial render, React creates a new fiber node for each element returned from the render method. In the following updates, fibers for existing React elements are reused and updated. The result of the phase is a tree of fiber nodes marked with side effects. The effects describe the work that needs to be done during the following commit phase. During this phase, React takes a fiber tree marked with effects and applies them to instances. It goes over the list of effects and performs DOM updates and other changes visible to a user. It's important to understand that the work during the first render phase can be performed asynchronously. React can process one or more fiber nodes depending on the available time, then stop to stash the work done and yield to some event. It then continues from where it left off. Sometimes, though, it may need to discard the work done and start from the top again. These pauses are made possible by the fact that the work performed during this phase doesn't lead to any user visible changes, like DOM updates. In contrast, the following commit phase is always synchronous. This is because the work performed during this stage leads to changes visible to the user, e.g. DOM updates. That's why React needs to do them in a single pass. Calling lifecycle methods is one type of work performed by React. Some methods are called during the render phase and others during the commit phase. Here's the list of lifecycles called when working through the first render phase. Unsafe underscore, component will mount, deprecated. Unsafe underscore, component will receive props, deprecated. Should component update, unsafe underscore, component will update, deprecated. Render. As you can see, some legacy lifecycle methods that are executed during the render phase are marked as unsafe from version 16. 3. They are now called legacy lifecycles in the docs. They will be deprecated in future 16. X. Releases and their counterparts without the unsafe prefix will be removed in 17. 0. You can read more about these changes and the suggested migration path here. Are you curious about the reason for this? Well, we've just learned that because the render phase doesn't produce side effects like DOM updates, React can process updates asynchronously to components asynchronously, potentially even doing it in multiple threads. However, the lifecycles marked with unsafe have often been.
This is also kind of concerning because, like, I didn't want to. I think it's better to move everything to a functional component instead of a class component in the React-pixi thing. But the problem is that maybe I should do that. I think it's gonna be like the way that I find out to move one to the other is gonna be slightly inefficient because you're gonna have to recreate the tree and update each time that the component mounts. Or maybe it's not a problem because it only happens. No, but the thing is that yeah, you're gonna have to recreate the tree each time that the component updates as well. That's the problem. So I think it makes a lot less efficient because with the class component, the component did update part of the or component will update. No, I think it's component did the update part that gets executed each time there is something that gets updated on the canvas. It doesn't recreate the fiber, the whole tree of the fiber. It just updates the container. But if I do it with the functional components, I couldn't figure out a way to do that because if you put that function inside of the use effect, it's not gonna have access to the mount node, which is the node that has to be created to mount the custom reconciler. So, and then mounting on the beginning of the function is not good as well because there's something else that happens inside of one of the use effects that requires you to have the mount node as well. And then if you just create the mount node outside, it doesn't update. It breaks at some point. And if you initialize it as null, then it's not the best as well, I think. Because obviously you can initialize it as null in the beginning, then create inside of one of the use effects, and the other one you just use it, the one that you initialize in the beginning to update. But then you can get in a situation where it's, and I think that's what happens, where it's still null because it doesn't go through the cycle. It just executes the two different use effects at the same time. So like the other alternative is just to create as an application in the beginning and create again inside of the other use effect, but that's also not very good, I think. So yeah, I couldn't figure out a way to make it happen. I think if I spend more time, I probably can figure out, but I'm not sure if like I don't feel like doing that now. Because I think it's better to just move on to the other stuff because I still have all like I want to fix this kind of things that are on my mind now. Mainly the the relationship between events between Matter.js and Pixi viewport. I think that's the main thing that I wanna fix, and then also the customization of the graph as well, which is going to involve passing props, which might be very complicated as well because, like, yeah, there's going to be a lot of stuff to think about, and also change the whole design of the website as well, which is going to be annoying. So I want to remove that stuff out of my mind first, like fix all of that, so I can like have only my focus only on the stuff that is going to matter, which is the compiler. And maybe at that point I should spend more time trying to see if I can move everything to a functional component and do something else instead of using flush sync to make the components amount, like to figure out a way to amount only the components that depend on the context. Maybe that's better as well. And yeah, it might be like a problem to leave it like this, because in the future when React updates again, it might be, I think it's unlikely that it's not going to be possible, because I think they're going to make sure that previous versions still work, but I think it's not ideal probably. It's probably better to update everything to the latest way. That makes sense, but I think I'm going to leave it like that for now, focus on the other stuff, and then go back later.
Being misunderstood and subtly misused. Developers tended to put the code with side effects inside these methods, which may cause problems with the new async rendering approach. Although only their counterparts without the unsafe prefix will be removed, they are still likely to cause issues in the upcoming concurrent mode, which you can opt out of. Here's the list of lifecycle methods executed during the second commit phase. Get snapshot before update. Component did mount. Component did update. Component will unmount. Because these methods execute in the synchronous commit phase, they may contain side effects and touch the DOM. Okay, so now we have the background to take a look at generalized algorithm used to walk the tree and perform work. Let's dive in. Render phase linked to this section. The reconciliation algorithm always starts from the topmost host root fiber node using the render root function. However, React bails out of, skips, already processed fiber nodes until it finds the node with unfinished work. For example, if you call set state deep in the components tree, React will start from the top but quickly skip over the parents until it gets to the component that had its set state method called. Main steps of the work loop linked to this section. All fiber nodes are processed in the work loop. Here is the implementation of the synchronous part of the loop. Work loop is yieldy if is yieldy, while next unit of work equals null, next unit of work equals perform unit of work, next unit of work, else. In the code above, the next unit of work holds a reference to the fiber node from the work in progress tree that has some work to do. As React traverses the tree of fibers, it uses this variable to know if there's any other fiber node with unfinished work. After the current fiber is processed, the variable will either contain the reference to the next fiber node in a tree or null. In that case, React exits the work loop and is ready to commit the changes. There are four main functions that are used to traverse the tree and initiate or complete the work. Begin work, complete unit of work, complete work. To demonstrate how they're used, take a look at the following animation of traversing a fiber tree. I've used a simplified implementation of these functions for the demo. Each function takes a fiber node to process, and as React goes down the tree, you can see the currently active fiber node changes. You can clearly see on the video how the algorithm goes from one branch to the other. It first completes the work for children before moving to parents. Note that straight vertical.
I think I'll look into the video after, see the exact order that happens.
Connections denote siblings, whereas bent connections denote children, e.g., B1 doesn't have children, while B2 has one child, C1. Here's the link to the video where you can pause the playback and inspect the current node and the state of functions. Conceptually, you can think of begin as stepping into a component and complete as stepping out of it. You can also play with the example and the implementation here as I explain what these functions do. Let's start with the first two functions, perform unit of work and begin work. Perform unit of work, work in progress, let next equals begin work in progress. If next equals null, next equals complete unit of work in progress, return next, function begin work in progress, console. Log, work performed for plus work in progress. Name, return work in progress. Child, the function perform unit of work receives a fiber node from the work in progress tree and starts the work by calling begin work function. This is the function that will start all the activities that need to be performed for a fiber. For the purposes of this demonstration, we simply log the name of the fiber to denote that the work has been done. The function begin work always returns a pointer to the next child to process in the loop or null. If there's a next child, it will be assigned to the variable next unit of work in the work loop function. However, if there's no child, React knows that it reached the end of the branch and so it can complete the current node. Once the node is completed, it'll need to perform work for siblings and backtrack to the parent after that. This is done in the complete unit of work function. Complete unit of work in progress, while true, let return fiber equals work in progress. Return, let sibling fiber equals work in progress. Sibling, next unit of work equals complete work in progress. If sibling fiber equals null, you can see that the gist of the function is a big while loop. React gets into this function when a work in progress node has no children. After completing the work for the current fiber, it checks if there's a sibling. If found, React exits the function and returns the pointer to the sibling. It will be assigned to the next unit of work variable and React will perform the work for the branch starting with this sibling. It's important to understand that at this point React has only completed work for the preceding siblings. It hasn't completed work for the parent node. Only once all branches starting with child node are completed does it complete the work for the parent node and backtracks. As you can see from the implementation, both and complete unit of work are used mostly for iteration purposes, whereas the main activities take place in the begin work and complete work functions. In the following articles in the series, we'll learn what happens for the click counter component and the span node as React steps into begin work and complete work functions. Commit phase linked to this section. The phase begins with the function complete root. This is where React updates the DOM and calls pre and post mutation lifecycle methods. When React gets to this phase, it has two trees in the effects list. The first tree represents the state currently rendered on the screen. Then there's an alternate tree built during the render phase. It's called finished work or work in progress in the sources and represents the state that needs to be reflected on the screen. This alternate tree is linked similarly to the current tree through the child and sibling pointers. And then there's an effects list, a subset of nodes from the finished work tree linked through the next effect pointer. Remember that the effect list is the result of running the render phase. The whole point of rendering was to determine which nodes need to be inserted, updated, or deleted, and which components need to have their lifecycle methods called. And that's what the effect list tells us, and it's exactly the set of nodes that's iterated during the commit phase. For debugging purposes, the current tree can be accessed through the current property of the fiber root. The finished work tree can be accessed through the alternate property of the host fiber node in the current tree. The main function that runs during the commit phase is commit root. Basically, it does the following: calls the get snapshot before update lifecycle method on nodes tagged with the snapshot effect. Calls the component will unmount lifecycle method on nodes tagged with the deletion effect. Performs all the DOM insertions, updates, and deletions. Sets the finished work tree as current. Calls component did mount lifecycle method on nodes tagged with the placement effect. Calls component did update lifecycle method on nodes tagged with the update effect. After calling the pre-mutation method get snapshot before update, React commits all the side effects within a tree. It does it in 2 passes. The first pass performs all DOM, host, insertions, updates, deletions, and ref unmounts. Then React assigns the finished work tree to the fiber root, marking the work in progress tree as the current tree. This is done after the first pass of the commit phase, so that the previous tree is still current during component will unmount, but before the second pass, so that the finished work is current during component did mount, update. In the second pass, React calls all other lifecycle methods and ref callbacks. These methods are executed as a separate pass so that all placements, updates, and deletions in the entire tree have already been invoked. Here's the gist of the function that runs the steps described above. Less than greater than copy function commit root, finished work, commit before mutation lifecycles. Commit all host effects, root, current, equals finished work, commit all lifecycles. Each of those subfunctions implements a loop that iterates over the list of effects and checks the type of effects. When it finds the effect pertaining to the function's purpose, it applies it. Pre-mutation lifecycle methods linked to this section. Here is, for example, the code that iterates over an effects tree and checks if a node has the snapshot effect. Commit before mutation lifecycles, while next effect equals null, const effect tag equals next effect. Effect tag. For a class component, this effect means calling the get snapshot before update lifecycle method. Commit all. The function basically defines the type of operation that needs to be done for a node and executes it. Less than greater than copy function, case placement and update, case update, commit work, case deletion, commit. It's interesting that React calls the component will unmount method as part of the deletion process in the commit deletion function. Post mutation lifecycle methods linked to this section. Commit all lifecycles is the function where React calls all remaining lifecycle methods component did update and component did mount. We're finally done. Let me know what you think about the article or ask questions in the comments. Check out the next article in the series in-depth explanation of state and props update in React. I have many more articles in the works providing in-depth explanation for scheduler, children reconciliation process and how effects list is built. I also have plans to create a video where I'll show how to debug the application using this article as a basis. Comments, 0.
I think this is the part that is kind of confusing. Because I think intuitively it makes more sense that you would do the next unit of work and perform unit of work and begin work on all of them until it gets to the bottom and only then starts completing the work. But based on this animation is not what happens. As here it goes to complete work in B1 already. So I don't understand really well why that's the case. I think I'll read these articles later. I'm just gonna read this one. And then go back to studying the source code in Pixi. I think what I'm trying to do, what I'm gonna try to do is to put the problem is that I can't really put the debugger on the matter.js unless I use the one that I have locally installed. And then I'm gonna have to refactor this stuff. That depends on matter.js. So maybe, yeah. Like I want to see if I can find a way to step over with the developer tools after I click, after the event gets triggered. So I think I'll try to do that after I read this article here. I'll be right back.
The how and why on React's usage of linked list in Fiber to walk the components tree. The main algorithm of the work loop in React's reconciler. Max Koretsky. Follow. Published in React in Depth. 10-minute read November 6, 2018. 18. React in Depth is moving away from Medium. This article, its updates and more recent articles are hosted on the new platform in Depth. Dev. To educate myself and the community, I spend a lot of time reverse engineering web technologies and writing about my findings. In the last year, I focused mostly on Angular sources which resulted in the biggest Angular publication on the web, Angular in Depth. Now the time has come to dive deep into React. Change detection has become the main area of my expertise in Angular, and with some patience and a lot of debugging, I hope to soon achieve that level in React. In React, the mechanism of change detection is often referred to as reconciliation or rendering, and Fiber is its newest implementation. Due to the underlying architecture, it provides capabilities to implement many interesting features like performing non-blocking rendering, applying updates based on the priority and pre-rendering content in the background. These features are referred to as time slicing in the concurrent React philosophy. Besides solving real problems of application developers, the internal implementation of these mechanisms has a wide appeal from the engineering perspective. There's such a wealth of knowledge in the sources that will help us grow as developers. If you Google React Fiber today, you're going to see quite a lot of articles in the search results. All of them, though, except for the notes by Andrew Clark, are pretty high-level explanations. In this article, I'll refer to this resource and provide an elaborate explanation for some particularly important concepts in Fiber. Once we've finished, you'll have enough knowledge to understand the work loop representation from a very good talk by Lynn Clark at ReactConf 2017. That's the one talk you need to see, but it'll make a lot more sense to you after you've spent a little time in the sources. This post opens a series on React's Fiber internals. I'm about 70% through understanding the internal details of the implementation and have 3 more articles on reconciliation and rendering mechanism in the works. I work as a developer advocate at Grid. If you're curious to learn about data grids or looking for the ultimate React data grid solution, give it a try with the guide. Get started with React Grid in 5 minutes. I'm happy to answer any questions you may have, and follow me to stay tuned. Let's get started. Setting the background. Fiber's architecture has 2 major phases: reconciliation, render, and commit. In the source code, the reconciliation phase is mostly referred to as the render phase. This is the phase when React walks the tree of components and updates state and props, calls lifecycle hooks, retrieves the children from the component, compares them to the previous children, and figures out the DOM updates that need to be performed. All these activities are referred to as work inside Fiber. The type of work that needs to be done depends on the type of the React element. For example, for a class component, React needs to instantiate a class, while it doesn't do it for a functional component. If interested, here you can see all types of work targets in Fiber. These activities are exactly what Andrew talks about here. When dealing with UIs, the problem is that if too much work is executed all at once, it can cause animations to drop frames. Now what about that all at once part? Well, basically, if React is going to walk the entire tree of components synchronously and perform work for each component, it may run over 16 moves available for an application code to execute its logic. And this will cause frames to drop, causing stuttering visual effects. Newer browsers and React Native implement APIs that help address this exact problem. The new API he talks about is the request idle callback global function that can be used to queue a function to be called during a browser's idle periods. Here's how you would use it by itself. If I now open the console and execute the code above, Chrome logs 49. 9 false. It basically tells me that I have 49. 9 moves to do whatever work I need to do and I haven't yet used up all allotted time, otherwise the deadline. DID timeout would be true. Keep in mind that time remaining can change as soon as a browser gets some work to do, so it should be constantly checked. Request idle callback is actually a bit too restrictive and is not executed often enough to implement smooth UI rendering, so React team had to implement their own version. Now if we put all the activities React performs on a component into the function perform work and use request idle callback to schedule the work, our code could look like this. We perform the work on one component and then return the reference to the next component to process. This would work, if not for one thing. You can't process the entire tree of components synchronously, as in the previous implementation of the reconciliation algorithm. And that's the problem Andrew talks about here. In order to use those APIs, you need a way to break rendering work into incremental units. So to solve this problem, React had to re-implement the algorithm for walking the tree from the synchronous recursive model that relied on the built-in stack to an asynchronous model with linked list and pointers. And that's what Andrew writes about here. If you rely only on the built-in call stack, it will keep doing work until the stack is empty. Wouldn't it be great if we could interrupt the call stack at will and manipulate stack frames manually? That's the purpose of React Fiber. Fiber is re-implementation of the stack, specialized for React components. You can think of a single fiber as a virtual stack frame. And that's what I'm going to explain now. A word about the stack. I assume you're all familiar with the notion of a call stack. This is what you see in your browser's debugging tools if you pause code at a breakpoint. Here are a few relevant quotes and diagrams from Wikipedia. In computer science, a call stack is a stack data structure that stores information about the active subroutines of a computer program. The main reason for having call stack is to keep track of the point to which each active subroutine should return control when it finishes executing. A call stack is composed of stack frames. Each stack frame corresponds to a call to a subroutine which has not yet terminated with a return. For example, if a subroutine named drawLine is currently running, having been called by a subroutine drawSquare, the top part of the call stack might be laid out like in the adjacent picture. Why is the stack relevant to React? As we defined in the first part of the article, React walks the components tree during the reconciliation, render phase and performs some work for components. The previous implementation of the reconciler used the synchronous recursive model that relied on the built-in stack to walk the tree. The official doc on reconciliation described this process and talk a lot about recursion. By default, when recursing on the children of a DOM node, React just iterates over both lists of children at the same time and generates a mutation whenever there's a difference. If you think about it, each recursive call adds a frame to the stack. And it does so synchronously. Suppose we have the following tree of components, represented as objects with the render function. You can think of them as instances of components. React needs to iterate the tree and perform work for each component. To simplify, the work to do is to log the name of the current component and retrieve its children. Here's how we do it with recursion. The main function that iterates over the tree is called walk in the implementation below. Here's the output we're getting. A1, B1, B2, C1, D1, D2, B3, C2. If you don't feel confident with recursions, check out my in-depth article on recursion. A recursive approach is intuitive and well suited for walking the trees. But as we discovered, it has limitations. The biggest one is that we can't break the work into incremental units. We can't pause the work at a particular component and resume it later. With this approach, React just keeps iterating until it processed all components and the stack is empty. So how does React implement the algorithm to walk the tree without recursion? It uses a singly linked list tree traversal algorithm. It makes it possible to pause the traversal and stop the stack from growing. Linked list traversal. I was lucky to find the gist of the algorithm outlined by Sebastian Markbridge here. To implement the algorithm, we need to have a data structure with 3 fields. Child, reference to the first child, sibling, reference to the first sibling, return, reference to the parent. In the context of the new reconciliation algorithm in React, the data structure with these fields is called Fiber. Under the hood, it's the representation of a React element that keeps a queue of work to do. More on that in my next articles. The following diagram demonstrates the hierarchy of objects linked through the linked list and the types of connections between them. So let's first define our custom node constructor, and the function that takes an array of nodes and links them together. We're going to use it to link children returned by the render method. The function iterates over the array of nodes starting from the last one and links them together in a singly linked list. It returns the reference to the first sibling in the list. Here is a simple demo of how it works. We also implement a helper function that performs some work for a node. In our case, it's going to log the name of a component. But besides that, it also retrieves the children of a component and links them together. Okay, now we're ready to implement the main traversal algorithm. It's a parent first, depth first implementation. Here is the code with useful comments. Although the implementation is not particularly difficult to understand, you may need to play with it a little to grok it. Grit here. The idea is that we keep the reference to the current node and reassign it while descending the tree until till we hit the end of the branch. Then we use the return pointer to return to the common parent. If we now check the call stack with this implementation, here's what we're going to see. As you can see, the stack doesn't grow as we walk down the tree. But if now put the debugger into the do work function and log node names, we're going to see the following. It looks like a call stack in a browser. So with this algorithm, we're effectively replacing the browser's implementation of the call stack with our own implementation. That's what Andrew describes here. Fiber is re-implementation of the stack, specialized for React components. You can think of a single fiber as a virtual stack frame. Since we're now controlling the stack by keeping the reference to the node that acts as a top frame, we can stop the traversal at any time and resume it later. That's exactly the condition we wanted to achieve to be able to use the new request idle callback API. Here's the code that implements work loop in React. As you can see, it maps nicely to the algorithm I presented above. It keeps the reference to the current fiber node in the next unit of work variable that acts as a top frame. The algorithm can walk the components tree synchronously and perform the work for each fiber node in the tree next unit of work. This is usually the case for so-called interactive updates caused by UI events, click, input, etc. Or it can walk the components tree asynchronously, checking if there's time left after performing work for a fiber node. The function should yield returns the result based on deadline did expire and deadline variables that are constantly updated as React performs work for a fiber node. The perform unit of work function is described in depth here. Thanks for reading. If you like this article, hit that.
I think I want to read this articles, this function and this article as well. Maybe this is the, no, it's not the same one. All of these articles I already read. I think I read them twice, probably. I just got all the researches for, or the searches for React Fiber, React Reconciler, all this stuff. And I opened all the articles and read them. I think probably a couple of times, but obviously you forget a lot of stuff. So and I think like the more times I read and the more times I try to understand, the easier it's gonna be to debug everything else and to think about everything else, because it's always gonna be connected with React, obviously, because I'm doing this stuff with Next.js.
Clap button below. It means a lot to me and it helps other people see the story. React Grid, the fastest and most feature-rich grid component from AgGrid. Written by Max Koretsky.
And I really liked the articles from this guy here. So shout out to him. Very good stuff. This one, sometimes it doesn't work. It doesn't capture the text.
Fiber principles, contributing to fiber number 7942. Seb Mark Bajay opened this issue October 11, 2016 11 comments. Seb Mark Bajay commented October 11, 2016 edited. I just wanted to document a few unique design patterns that apply to fiber, but not necessarily anything else. I'll start here. You may mutate the fiber that you're working on during begin work and complete work phases, but you may not have any other global side effects. If you need a global side effect, that have to be moved to the commit work phase. Fiber is a fixed data structure. It shares the same hidden class. Never add fields outside of construction in React Fiber. Nothing in the reconciler uses dynamic dispatch, i.e., we don't call a first class function, except for user code such as ref callbacks, functional components, render methods, etc. The rest is a static function available in a closure, i.e., use my helper, obj, instead of obj. My helper, anytime we need to branch logic, we use a switch statement over a tag, which is a number that indicates which type of object we're dealing with and which branch to take. See pattern matching. Many modules are instantiated with a host config object. It is a single constructor that gets called on initialization time. This should be inlineable by a compiler. Nothing in Fiber uses the normal JS stack, meaning it does use the stack, but it can be compiled into a flat function if needed. Calling other functions is fine, the only limitation is that they can't be recursive. If I can't use recursion, how do I traverse through the tree? Learn to use the singly linked list tree traversal algorithm, e.g., parent first, depth first, let root equals fiber, let node equals fiber, while true, do something with node if, node, child, node equals node, child, continue, if, node equals root, return, while, node, sibling, if, node return equals root, return, node equals node, sibling. Why does it need to be this complicated? We can use the normal JS stack for this, but anytime we yield in a request idle callback, we would have to rebuild the stack when we continue. Since this only lasts for about 50 milliseconds when idle, we would spend some time unwinding and rebuilding the stack each time. It is not too bad. However, everything along the stack would have to be aware of how to unwind when we abort in the middle of the workflow. It is plausible we could do this at the level of OCaml algebraic effects, but we don't currently have all the features we need and we don't get the performance trade-offs we want out of the box ATM. This is a plausible future way forward though. Most code lives outside of this recursion, so it doesn't matter much for most cases. Most of what React is in the space of what the normal stack does. E.g., memoization, error handling, etc. Using the normal stack too just makes it more difficult to get those to interact. Everything we put on the stack we generally have to put on the heap too because we memoize it. Maintaining the stack and the heap with the same data is theoretically less efficient. That said, all of these optimizations might be moot because JS stacks are much more efficient than JS heaps. One thing that I wanted to try was to compile React components to do work directly on these data structures, just like normal programming languages compile to make mutations, etc. To the stack, I think that's where the ideal implementation of React is. Let's just try it and see how it goes. DCC at Spicy J, Gayer and at ACD Light. Keys, Chikoxizi, Asolov, Romana, Alex Wilson, Carly Matthews, Leo Isis, Luigi PLR, Chris Lloyd, David G. Tong, and 224 more reacted with thumbs up emoji. Yangshan, Boris Yankov. Aren't you just working around the lack of threads in the language? Yes and no. It is true that we don't have a good option in JavaScript to run threads, and that is a huge problem. We tried exploring various options of running in web workers, Parallel.js, tried to propose shared immutable persistent data structures to the language, experimented with custom VM tweaks, etc. JavaScript, the language, isn't very suitable for this because of mutable shared runtimes like prototypes. The ecosystem isn't ready for it because you have to duplicate code loading and module initialization across workers. Garbage collectors are not as efficient as they currently are if they have to be thread safe, and VM implementers seem to be unwilling to bear the implementation cost of persistent data structures. Shared mutable typed array seems to be moving along, but requiring all data to go through this layer seems to be unfeasible in the ecosystem today. Artificial boundaries between different parts of the code base also doesn't work very well and introduces unnecessary friction. Even then you have lots of JS code like utility libraries that have to be duplicated across workers, which leads to slower startup time and memory overhead. So, yes, threads are likely out of the question until we can target something like WebAssembly. However, an interesting realization is that there are other benefits of the Fiber architecture that are applicable whether you have threads or not. Component kit that runs on native does work using threads, for example. It is able to start doing high priority work in one thread while a lower priority thread is still happening, leading to a much simpler implementation. However, there are some limitations. You can't safely abort the background thread. Aborting and restarting a thread is not very cheap. In many languages, it is also not safe because you could be in the middle of some lazy initialization work. Even though it is effectively interrupted, you have to continue spending CPU cycles on it. One solution is to do the same thing that Fiber does, make an API that has yield points so that you can unwind the stack safely. Then check a flag periodically if you should abort. That is effectively what Fiber does too. Another limitation is that since you can't immediately abort a thread, you can't be sure if two threads are processing the same component at the same time. This leads to some limitations such as not being able to support stateful class instances, like React component, although that might be a good thing for other reasons. Another thing that threads don't automatically buy you is the ability to resume part of the work. You can't just memoize part of the work that you've done in one thread and reuse it in another. You can certainly implement that with threads, but you'd end up with similar complexity as Fiber on top of the threads. Threads have a slight benefit that you can start the next work slightly earlier because you can interject instructions while the background thread is still powering down. However, because our yield points are frequent enough by default, we don't think that will matter for Fiber. Therefore, yes, we are writing a more complex implementation because we're lacking threads in JavaScript, but because we're forced to deal with that, we'll end up with better features than if we simply relied on threads for scheduling. What about parallelism? It is true that threads can get you parallelism. However, this has nothing to do with scheduling for responsiveness. You generally don't want to spend one CPU processing work that was already aborted because higher priority work arrived. That doesn't buy you anything at all. Instead, what you really want is to calculate independent work in different threads. For example, two React siblings can be calculated in parallel threads since they're disconnected. If we had access to threads, that's what we would do. However, everything about Fiber is still valid for scheduling purposes in that architecture, even if we use threads for parallelism of subtrees. So, in conclusion, no, we're not just working around limitations in a language. Note, this is not to say that you should choose cooperative scheduling over threads in your project use case. It's just that for our particular use case it made sense. Threads still make sense in many other cases. Vazant K, Sigmus, Mark Erickson, Cobro 4, Apps for Artists, Carl Hawkey, Kenneth Post. Okay, so cooperative scheduling might have some benefits over preemptive threads, but couldn't you just use generator functions like other scheduling frameworks have done? No, there's two reasons for this. Generators doesn't just let you yield in the middle of a stack. You have to wrap every single function in a generator. This not only adds a lot of syntactic overhead but also runtime overhead in any existing implementation. It's fair that the syntax might be more helpful than not, but the perf issue still stands. The biggest reason, however, is that generators are stateful. You can't resume in the middle of it. Function to work A, B, C, var x equals do expensive work A, yield, var y equals x plus do expensive work B, B, yield, var z equals y plus do expensive work C, C, return z. If I want to execute this across multiple time slices, I can just step through this. However, if I get an update to B when I have already completed do expensive work A, and do expensive work B, B, but not do expensive work C, C, there is no way for me to reuse the value x. I.e., to skip ahead to do expensive work B with a different value for B, but still reuse the result of do expensive work A. This is important to React since we do a lot of memoization. It is plausible that you can add that as a layer around, but then you're really not gaining much from the use of generators. There are also languages that have generators that are designed for a more functional use case that has this capability. JS is not one of them. Vazant K, a weary, Cobro 4. Okay, but what about OCaml's algebraic effects then? Buckle script can compile them. There is some non-trivial overhead in the JS version, but assuming that would be okay. To use algebraic effects in OCaml in this way, I think we would need to clone each fiber so that we can resume it. It is possible that a compiler could reuse an immutable stack frame, Fiber, without copying, but that's not how it works now. Without that, we only get limited benefits. We would also end up with lots of nested handlers which would add to the overhead and also add linear search time to find the top handler when we do yield. Besides, to support the existing React API, we need a set of features that overlap with the implementation of fibers, such as return pointers, so by combining them we get some benefits. I do have high hopes that one day we can just use effects for our use cases internally, but we could also use it to make an even simpler React API itself. However, for now, I think that it is probably easier to have lower level control even though the complexity is higher. I do look forward to seeing other implementations that prioritize implementation simplicity or using complex compilers to solve the same problems. Vazant K, Hufeng, A Weary, Develop It, Cobro 4, Carl Hawkey, Ryan C. Collins, Kenneth Postigo. Vazant K, Hufeng, A Weary, Develop It, Cobro 4. Hi. Thanks for writing up these thoughts. They're great. I realize it's been a few weeks since you wrote this, but there's one bit I didn't quite understand. I may be misreading or missing something, but under the generator functions section, you say. The biggest reason, however, is that generators are stateful. You can't resume in the middle of it. Function to work A, B, C, var x equals do expensive work A, yield, var y equals x plus do expensive work B, B, yield, var z equals y plus do expensive work C, C, return z. If I want to execute this across multiple time slices, I can just step through this. However, if I get an update to B when I have already completed do expensive work A, and do expensive work B, B, but not do expensive work C, C, there is no way for me to reuse the value x. I.e., to skip ahead to do expensive work B with a different value for B, but still reuse the result of do expensive work A. This is important to React since we do a lot of memoization. Wouldn't memoization actually make this a non-issue? Assuming do expensive work A is a memoized function, then calling it again with the same value would be fast, effectively allowing you to skip the heavy work and continue to do expensive work B. I don't know what these do expensive work functions represent, so maybe it's not possible to memoize them in this way. JROP, NE Small Town, Fabian Cook, and Brandon Lane. It really more of a placeholder for other work within this generator that may be expensive. The problem with memoization of do expensive work A is that React doesn't have an opportunity to inject memoization there, including its local memoization strategy using parent context and keys. You could use a global memoization for that method, but then you end up with cache invalidation problems instead. B. Vaughan, Con Antonikos, Jessidia, Tuchik 4, Rathius, Kodik, NE Small Town, Dukale, Yar. I'm a little confused. Why there is no opportunity? We could do something like const do expensive work equals lodash, memoize, function, do expensive work A, and can just do local memoization strategy in the local function. Function to work A. At any small town if so, I think it will work too. Maybe the problem is it will rely too much on global cache, or not elegant than the fiber structure. Nicola's added the React core team opened by a member of the React core team labeled Jan 8, 2020. I have to say this is an excellent explanation. BNI and JD Nicol SC reacted with thumbs up emoji. Orphan commented Deck 1, 2020. At any small town if so, I think it will work too. Inside Fiber, in-depth overview of the new reconciliation algorithm in React. The how and why on everything from React elements to Fiber nodes. React in-depth is moving away from Medium. This article, its updates and more recent articles are hosted on the new platform in-depth. Dev, React is a JavaScript library for building user interfaces. At its core lies the mechanism that tracks changes in a component state and projects the updated state to the screen. In React we know this process as reconciliation. We call the set state method and the framework checks if the state or props have changed and re-renders a component on UI. React docs provide a good high-level overview of the mechanism, the role of React elements, lifecycle methods and the render method, and the diffing algorithm applied to a component's children. The tree of immutable React elements returned from the render method is commonly known as the virtual DOM.
I think I'm actually gonna stop after I read this article. And because it's almost 3 hours and a half already. And then I'm gonna step through the Pixi viewport and figure out the debugger endpoints after I trigger the effect here. I'm gonna see if I can put debugger endpoints or breakpoints so that when I click to activate the effect, I know what is going to happen. I can step through whatever is happening. And I'm probably going to step over these other breakpoints that I put here already a couple of more times, just like I did with React, to really understand like everything that is happening once is initializing these classes and how they're connected, and like get more of a clear picture in my mind of what is happening and how it's gonna do the calculations on the canvas and how it sets up the events. Maybe I'll probably write down here as well, I think, like what events are being triggered and not triggered, but how it's setting up the events in the beginning, so that I understand. I think I'm gonna try to clarify like what is the key fundamental issue, and should think about a way to the best way forward to solve the issue. Obviously, the key fundamental issue is the conflict between the events in the two different libraries, but like what are the nuances that are involved in that, both in the event listeners and on React, and then how can I go about like what kind of stuff do I have to investigate or change in order to be able to test different things to see how I can solve this. So I have both events. The goal for now, the next challenge is to have both events at the same time, to be able to zoom in the canvas and move the canvas around, and also to interact with the elements of the canvas. Once I figure that out, then I'm going to improve the visualization by changing the code with Matter.js for the shapes to just make the line better and put the constraints, and then see if I can customize the visualization as well. After I'm done with all of this stuff, then the next challenge is going to be the compiler. I think at that point, after I redo the user interface, then I'm going to think about like which direction I'm going to go, if I'm going to go back and try to optimize the whole cycle so that I'm not using flush sync and I'm using a functional component, so that is more efficient, or if I'm going to go try to solve the compilers. I think it's more likely that I'm going to try to solve the compilers first because it's more interesting and more useful, and then I can probably use that to like use my own visualizations to see if I can improve later. I think that's probably the best approach.
That term helped explain React to people early on, but it also caused confusion and isn't used in the React documentation anymore. In this article, I'll stick to calling it a tree of React elements. Besides the tree of React elements, the framework has always had a tree of internal instances, components, DOM nodes, etc., used to keep the state. Starting from version 16, React rolled out a new implementation of that internal instances tree and the algorithm that manages it code named Fiber. To learn about the advantages which the Fiber architecture brings, check out the how and why on React's usage of linked list in Fiber. This article would take me a lot longer to write and would be less comprehensive without the help of Dan Abramoff. This is the first article in a series aimed at teaching you internal architecture of React. In this article, one wants to provide an in-depth overview of important concepts and data structures relevant to the algorithm. Once we have enough background, we'll explore the algorithm and main functions used to traverse and process the Fiber tree. Next articles in the series will demonstrate how React uses the algorithm to perform initial render and process state and props updates. From there, we'll move on to the details of the scheduler, the child reconciliation process, and the mechanism of building an effects list. Follow me to stay tuned. I'm going to give you some pretty advanced knowledge here. I encourage you to read it to understand the magic behind the inner workings of concurrent React. This series of articles will also serve you as a great guide if you plan to start contributing to React. I'm a strong believer in reverse engineering, so there will be a lot of links to the sources from the recent version 16.6.0. It's definitely quite a lot to take in, so don't feel stressed if you don't understand something right away. It takes time as everything worthwhile. Note that you don't need to know any of it to use React. This article is about how React works internally. I work as a developer advocate at AgGrid. If you're curious to learn about data grids or looking for the ultimate React data grid solution, get in touch or give it a try with the guide.
I think I disagree with this statement, and I think that's a very big problem we have now, and it's only going to be more problematic because it's just a half truth of the you don't really need to know this stuff to use React. Like this sort of true, but is also not true, because the only reason why you don't need to know this stuff is because someone else knows it. So that is very similar to the car situation, where you don't need to know exactly how the car works to drive a car, but it's exponentially better if you understand how the car works, because what happens when the car breaks is that you have to call someone to fix it. So that intelligence of the collective consciousness works together to make these things possible. But like if you don't understand it, the problem is going to be that every time you have a bug, because you don't have the fundamental understanding of what's happening under the hood, it's going to take you a lot longer to debug this stuff. Is exactly the thing that the reason why I spend all this time trying to understand this is because, like, the reason why coding is difficult is not because of the syntax, obviously. I think everyone knows that. It's because, like, there's this ocean of knowledge hidden underneath on all this complexity, and you're working with the concepts on the surface. So when something breaks, the difference between the experienced person and the not experienced one is going to be how fast they fix the issue, because the experienced person is going to have a better understanding of all the complexity that is hidden under the hood. And that's going to be always where the problems are. So if you, like, you don't need to understand your code, but you actually do, because you're going to run into problems because just the nature of the thing. And then once you run into problems, you're going to be stuck because there's a lot of black boxes in your knowledge, so you're not going to be able to fix. And I think that's a huge issue, and it's one of the reasons why I'm trying to build this stuff that I'm doing now, because I think the way to solve that is to bring more clarity and make it more, because the efficiency in which you understand things has to grow in the same rate as the complexity of the system grows, I think, because they are obviously directly correlated. So, and that's the main, like, one of the fundamental paradoxes of AI is that once the complexity increases so much that nobody understands what's going on, it's not like it's still gonna work for some time, but then the problem is once there is an issue, it breaks everything else, because it's everything built on a house of cards, and there's no one you can call to answer the question of what is happening, because no one understands what's going on under the hood on how machine learning models think. Because you understand the structure that makes them possible, but you don't understand how that structure creates the patterns of thinking that are going to produce stuff. And that's the fundamental problem. So I think it is required to understand, and you should aim to understand as much as possible. But obviously it's like a funnel, there's hierarchy, so you should start at the surface, and then the process of learning something is figuring out what are the relative symmetries that make up the geometrical structure of the informational field of the stuff that you're trying to learn. So you start in the surface, and then you ask questions, and you keep in mind that there's always going to be a boundary, because that's the essence of the electromagnetic field is a polarity, so it's going to be a symmetry, and that symmetry is going to have other symmetries that are connected to it, and the relationship between those symmetries that are going to make up the geometrical structure of that information. So your goal should be to over time clarify more and more how all the black boxes are connected. And I think the reason why people say it's not necessary, it's just I don't know, it's like kind of a coping mechanism, I think.
Get started with React Grid in 5 minutes. I'm happy to answer any questions you may have. Setting the background. Here's a simple application that I'll use throughout the series. We have a button that simply increments a number rendered on the screen. And here's the implementation. You can play with it here. As you can.
I think that's the issue that I have with this kind of thinking, is because you're just denying the problem instead of trying to fix it. That's why. So when you say like it's not necessary for people to learn this stuff, is like you're trying to hide away. It's like you're in a plane or in a boat, and the boat's gonna crash, and instead of thinking about how can I move the direction of the boat so it doesn't crash, I just say, don't worry everyone, just look the other way. So it's kind of like that kind of thinking for me, where like you don't have to understand the complexity, just look away, but the boat is gonna crash if you tell people that. So it's better that you tell them the truth, which is like there's no way around it, you're gonna have to understand it. And the answer is, how do you create the best framework so that you're always moving to the direction of increasing your understanding, while at the same time not being overwhelmed by all the ocean of complexity that you don't understand. And I think that's the problem with Dunning-Kruger, is because a lot of people are arrogant about the stuff they know because they don't have the kind of mindset. So because their brains trying to make them rationalize their comfort zone, so it's much easier to become arrogant so that you don't have to face the ocean of complexity, because then you have to sit under uncertainty, and then that makes you spend a lot of more energy and take more risk, because you always have to reflect on your identity. So
You can see it's a simple component that returns two child elements button and span from the render method. As soon as you click on the button, the state of the component is updated inside the handler. This, in turn, results in the text update for the span element. There are various activities React performs during reconciliation. For example, here are the high-level operations React performs during the first render and after state update in our simple application. Updates count property in the state of click counter. Retrieves and compares children of click counter and their props. Updates props for the span element. There are other activities performed during reconciliation like calling lifecycle methods or updating refs. All these activities are collectively referred to as work in the fiber architecture. The type of work usually depends on the type of React element. For example, for a class component, React needs to create an instance, while it doesn't do that for a functional component. As you know, we have many kinds of elements in React, e.g., class and functional components, host components, DOM nodes, portals, etc. The type of React element is defined by the first parameter to the create element function. This function is generally used in the render method to create an element. Before we begin our exploration of the activities in the main fiber algorithm, let's first get ourselves familiar with the data structures used internally by React. From React elements to fiber nodes, every component in React has a UI representation we can call a view or a template that's returned from the render method. Here's the template for our click counter component. Once a template goes through the JSX compiler, you end up with a bunch of React elements. This is what's really returned from the render method of React components, not HTML. Since we're not required to use JSX, the render method for our click counter component can be rewritten like this. The calls to React, create element, in the render method will create two data structures like this. You can see that React adds the property $$ type to these objects to uniquely identify them as React elements. Then we have properties type, key and props that describe the element. The values are taken from what you pass to the React, create element, function. Notice how React represents text content as children of the span and button nodes. And how the click handler is part of the button element props. There are other fields on React elements like the ref field that are beyond the scope of this article. The React element for click counter doesn't have any props or a key. Fiber nodes. During reconciliation, data from every React element returned from the render method is merged into the tree of fiber nodes. Every React element has a corresponding fiber node. Unlike React elements, fibers aren't recreated on every render. These are mutable data structures that hold component state and DOM. We discussed earlier that depending on the type of React element, the framework needs to perform different activities. In our sample application, for the class component's click counter, it calls lifecycle methods and the render method, whereas for the span host component, DOM node, it performs DOM mutation. So each React element is converted into a fiber node of corresponding type that describes the work that needs to be done. You can think of a fiber as a data structure that represents some work to do, or, in other words, a unit of work. Fiber's architecture also provides a convenient way to track, schedule, pause, and abort the work. When a React element is converted into a fiber node for the first time, React uses the data from the element to create a fiber in the create fiber from type and props function. In the consequent updates, React reuses the fiber node and just updates the necessary properties using data from a corresponding React element. React may also need to move the node in the hierarchy based on the key prop or delete it if the corresponding React element is no longer returned from the render method. Check out the child reconciler function to see the list of all activities and corresponding functions React performs for existing fiber nodes. Because React creates a fiber for each React element, and since we have a tree of those elements, we're going to have a tree of fiber nodes. In the case of our sample application, it looks like this. All fiber nodes are connected through a linked list using the following properties on fiber nodes: child, sibling, and return. For more details on why it works this way, check out my article The How and Why on React's usage of linked list in fiber if you haven't read it already. Current and work in progress trees. After the first render, React ends up with a fiber tree that reflects the state of the application that was used to render the UI. This tree is often referred to as current. When React starts working on updates, it builds a so-called work in progress tree that reflects the future state to be flushed to the screen. All work is performed on fibers from the work in progress tree. As React goes through the current tree, for each existing fiber node, it creates an alternate node that constitutes the work in progress tree. This node is created using the data from React elements returned by the render method. Once the updates are processed and all related work is completed, React will have an alternate tree ready to be flushed to the screen. Once this work in progress tree is rendered on the screen, it becomes the current tree. One of React's core principles is consistency. React always updates the DOM in one go. It doesn't show partial results. The work in progress tree serves as a draft that's not visible to the user, so that React can process all components first and then flush their changes to the screen. In the sources, you'll see a lot of functions that take fiber nodes from both the current and work in progress trees. Here's the signature of one such function. Each fiber node holds a reference to its counterpart from the other tree in the alternate field. A node from the current tree points to the node from the work in progress tree and vice versa. We can think of a component in React as a function that uses the state and props to compute the UI representation. Every other activity like mutating the DOM or calling lifecycle method should be considered a side effect or simply an effect. Effects are also mentioned in the docs. You've likely performed data fetching, subscriptions, or manually changing the DOM from React components before. We call these operations side effects or effects for short because they can affect other components and can't be done during rendering. You can see how most state and props updates will lead to side effects. And since applying effects is a type of work, a fiber node is a convenient mechanism to track effects in addition to updates. Each fiber node can have effects associated with it. They're encoded in the effect tag field. So effects in fiber basically define the work that needs to be done for instances after updates have been processed. For host components, DOM elements, the work consists of adding, updating, or removing elements. For class components, React may need to update refs and call the component did mount and component did update lifecycle methods. There are also other effects corresponding to other types of fibers. Effects list. React processes updates very quickly, and to achieve that level of performance, it employs a few interesting techniques. One of them is building a linear list of fiber nodes with effects for quick iteration. Iterating the linear list is much faster than a tree, and there's no need to spend time on nodes without side effects. The goal of this list is to mark nodes that have DOM updates or other effects associated with them. This list is a subset of the finished work tree and is linked using the next effect property instead of the child property used in the current and work in progress trees. Dan Abramoff offered an analogy for an effects list. He likes to think of it as a Christmas tree, with Christmas lights binding all effectful nodes together. To visualize this, let's imagine the following tree of fiber nodes where the highlighted nodes have some work to do. For example, our update caused C2 to be inserted into the DOM.
pretty sure that's the article that I already read now, but whatever. I'm just gonna read it again, and after I'm done with this, I'm gonna stop this stream.
B2 and C1 to change attributes, and B2 to fire a lifecycle method. The effect list will link them together so React can see other nodes later. You can see how the nodes with effects are linked together. When going over the nodes, React uses the first effect pointer to figure out where the list starts. So the diagram above can be represented as a linear list like this. As you can see, React applies effects in the order from children up to parents. Root of the fiber tree. Every React application has one or more DOM elements that act as containers. In our case, it's the div element with the ID container. React creates a fiber root object for each of those containers. You can access it using the reference to the DOM element. This fiber root is where React holds the reference to a fiber tree. It is stored in the current property of the fiber root. The fiber tree starts with a special type of fiber node which is host root. It's created internally and acts as a parent for your topmost component. There's a link from the host root fiber node back to the fiber root through the state node property. You can explore the fiber tree by accessing the topmost host root fiber node through the fiber root. Or you can get an individual fiber node from a component instance like this. Fiber node structure. Let's now take a look at the structure of fiber nodes created for the click counter component. And the span DOM element. There's quite a lot of fields on fiber nodes. I described the purpose of the fields alternate, effect tag, and next effect in previous sections. Let's now see why we need others. State node holds a reference to the class instance of a component, a DOM node or other React element type associated with the fiber node. In general, we can say that this property is used to hold the local state associated with.
Another thing that I just thought about now is that maybe is unrelated to this stuff, but just came up in my mind. A lot of the times people think that this, like, they see other people and they think about like how is that person very disciplined. But I think what happens is that I think it is related to the stuff that I was talking about, the ocean of information. It's just that what looks very difficult for some person is going to be very easy for the other one. And the difference between them is how much of the subconscious information they were able to capture over time. So I think that's the thing that happens with people a lot. Is that because we are always comparing ourselves to other people? Because your biology is designed to make you seek status and power because that allows you to reproduce. So you're always comparing yourself with other people, and because of that, because everyone is at different levels in the journey of how much they know about something, when you look at someone that is very good at what they do, it may seem like they have this incredible discipline, but that's just because over time, over the years of them doing all this stuff, they were able to capture or to download all the information into their subconscious mind over time. Because that's what's happening when you're learning. It's like you're a database and you're downloading the information in your system. So over time, the information gets attached or gets cached in your biological structure, which is in your intuition. So the more information you have on your subconscious about the stuff that you're doing, the easier it becomes for you to do it, because then it doesn't require effort, because effort is the thing that is forcing yourself out of your comfort zone. And the reason why that's hard is because that goes against gravity, because gravity and conservation of energy and mass is always going to make it so that whatever is the state of your subconscious mind at the present moment in time is going to be the thing that is more likely to happen next, because that's the essence of gravity. So when you capture enough information about a subject, what's going to happen is that your subconscious mind is in alignment, is in sync with that thing, because you have a lot of information of that stuff in the subconscious mind, and then it takes less energy for you to do the same output because you have more information in your system that is aligned with that. So the same unit of effort for two different people is going to feel very different, because the person that has all this stuff in their subconscious mind that is related to that thing is going to spend a lot less energy doing that than the person that doesn't. And that's why a lot of the times when you look at someone and they're doing something for hours and it's very easy to them, it's just because they spend a lot more time downloading information about that than you did. So it's not really discipline. It's just the way that their systems are aligned.
With a fiber. Type defines the functional class associated with this fiber. For class components, it points to the constructor function. For DOM elements, it specifies the HTML tag. I use this field quite often to understand what element of fiber node is related to.
I think that discipline does play a part when you're shifting the directions. I think that's the thing. Because in the beginning of something, of anything that you're going to do that's going to be new, is always going to require you to have the discipline, because then it's when you're trying to change the direction you're going. So when you're trying to change the informational field, the gravitation in your body, to be aligned with something else, then that's going to require effort. And that's the stuff that you don't have a lot. So it's going to be harder by definition. But I think the difference between the people that do it and don't do it is the awareness of how much they are exerting that. So like you should be able to go for longer with something that you're used to, and like allow yourself to not do as much in something that feels uncomfortable. Because that way, over time, you're going to be able to download that. And then it's like a funnel. The more you download, the more you're capable of doing without feeling that you're exerting effort. And I think that that's very clear. Like, it's more and more clear to me when I'm studying this stuff, that a lot of the times, and your mind's going to come up with a bunch of rationalizations for you to not do the stuff that takes effort, because that's spends a lot more energy and is a lot harder to do it. So I think that a good strategy is just to allow yourself to not do as much when something feels very hard, because that way, and you expose yourself over time with that stuff that feels very hard, because that way you're like slowly start downloading that in your subconscious, and then it becomes easier and easier, and then over time it feels like you do less effort, but you make more happen because you downloaded the information.
Tag defines the type of the fiber. It's used in the reconciliation algorithm to determine what work needs to be done. As mentioned earlier, the work varies depending on the type of React element. The function create fiber from type and props maps a React element to the corresponding fiber node type. In our application, the property tag for the click counter component is one which denotes a class component, and for the span element, it's 5 denoting a host component. Update QA of state updates, callbacks, and DOM updates. Memorize state of the fiber that was used to create the output. When processing updates, it reflects the state that's currently rendered on the screen. Memorize props of the fiber that were used to create the output during the previous render. Pending props that have been updated from new data in React elements and need to be applied to child components or DOM elements. Key unique identifier with a group of children to help React figure out which items have changed, have been added or removed from the list. It's related to the lists and keys functionality of React described here. You can find the complete structure of the fiber node here. I've omitted a bunch of fields in the explanation above. Particularly, I skipped the pointers child, sibling, and return that make up a tree data structure which I described in my previous article. And a category of fields like expiration time, child expiration time, and mode that are specific to scheduler. React performs work in two main phases, render and commit. During the first render phase, React applies updates to components scheduled through set state or React. Render and figures out what needs to be updated in the UI. If it's the initial render, React creates a new fiber node for each element returned from the render method. In the following updates, fibers for existing React elements are reused and updated. The result of the phase is a tree of fiber nodes marked with side effects. The effects describe the work that needs to be done during the following commit phase. During this phase,
I think another thing on that is that, like, a lot of the times, and this is hard for me, obviously, for everyone, I think, that people fail at doing something, let's say, is because they, I think that like people are too hard on themselves on this stuff, that because your mind is naturally, your body is naturally against you moving that other direction. So like when you put, it's a weird thing that happens because you put too much pressure on yourself to be that, and paradoxically that makes you never be that way because you're not allowing yourself to suck at something. So, or to quit like after a very short period of time. And it's very interesting how that happens. So I think a lot of the time people put the expectation like they're harder on themselves to be disciplined, but then that makes it so that they work less because what happens is that their body is tricking them, and this happens to me obviously as well. Your body tricks you into thinking that like you have to work this amount or have to do this amount, and then what happens in reality is that you work a lot less than that because you're like sabotaging yourself to not do the stuff that is gonna take you out of your comfort zone. It's very interesting how that happens. And if instead of doing that you just said like I'm just gonna do this thing for 2 minutes or 5 minutes, that forces my brain into an uncomfortable state that I'm gonna feel like I'm exerting a lot of energy and I'm sucking at something, and then I'm just gonna relax. After that, if you did that, paradoxically, you would do a lot more than the first scenario, because then over time you would capture that information and you would like slowly go outside of your comfort zone every single day, and then over time, that from a person that is on the outside is gonna look that it was very easy for you, but in reality, it's just because you spend more time slowly getting out of your comfort zone, and then over time you become very good. And then once you reach that point, it looks like you're doing a lot of work, but you're actually not doing a lot of work because you're just maintaining the stuff that you downloaded over time.
React takes a fiber tree marked with effects and applies them to instances. It goes over the list of effects and performs DOM update.
But it's very extremely difficult to reach the balance, and I think that's also because of the way that the systems have to work, because like we need to put systems in place that force people to do stuff, because most people are not going to do things by themselves because the nature of the collective consciousness, where it creates a hierarchy. So 20% of people are going to do the work regardless of whether or not someone tells them to do. And those people are the ones that lead the other 80% that doesn't do. And that's why you need to have rules and systems that force people to put in the work even when they don't feel like it. So that becomes very hard, because then it becomes the whole nuance thing of like people are forced to work a certain amount, even though that's not going to be the most efficient, because the most efficient way would be for them to go with the flow of their body. But then the problem is, if you only allow people to go with the flow of their body, 80% of people are going to rationalize and do less work. And that's the whole problem with the remote versus in-person, I think, because it plays on the nuance, as always. Figuring out what are the line of nuance that is going to allow you to optimize, because this is the issue. You can't force creativity because it goes against the rules of the system. And obviously scientific thinking and the paradigm of market economy is based on the rational thinking, but then you lose the other side of the symmetry, which is the creative thinking. And creative thinking can allow you to evolve exponentially because it's not linear. So, but you can't force it to happen. That's the problem. And this is what the weird paradox of this, where a lot of times people can't do that because then they're forced based on the system to work, choose force instead of using power. Force is just when you're trying to use discipline or work really hard in something. But then that's not very good, because you would be much better off by using power, which is just creativity. And the reason why human beings dominate the planet It's not because we are very strong, it's because we are very powerful. So power comes from creativity, and I think David Hawkins talks about this, I think, which is Power versus Force, the book, very good. And I think that's the shifting paradigm. And like Force is using discipline and that kind of stuff to do something, and Power is using creativity. But it's actually the combination of both, obviously, that is the optimal, I think, state. But I think you have to go full circle. Like the only way to truly be able to do that is by exerting a lot of force first, and only after you exert a lot of force, then you are able to use power. I think that has to be the case, because otherwise your system is always going to rationalize for the other side, which is to not do anything. So you kind of have to go through the cycle.
It's another change is visible to a user. It's important to understand that the work during the first render phase can be performed asynchronously. React can process one or more Fiber nodes depending on the available time, then stop to stash the work done and yield to some event. It then continues from where it left off. Sometimes, though, it may need to discard the work done and start from the top again. These pauses are made.
Okay, I'm gonna have to stop now. It's whatever, because almost over. So probably gonna, I'm not sure when I'm gonna come back, probably tomorrow, but maybe not. I think it's gonna depend on how much I'm gonna try to spend a bunch of time stepping over this, but yeah, probably come back tomorrow. If not, I will come back soon and continue to work on this stuff. So see you then.